Hi, Natty.
Can you hear me now?
I can hear you now.
But can I share the screen and check it?
Let's do that. Great.
Okay, am I good now?
Yeah.
You don't see the presenter view, do you?
I do not see the presenter view now. I just see the presentation.
Now I'm going to open the other one.
Hi, Ofer.
Hi, I see that you've already made me the co-host. Great. So I guess I'm all set.
Yeah.
Yes. So let me know if you want me to describe the rules or if you're going to do it before the beginning or whichever.
I think I'll make I'll make the announcement again, if that's okay.
Okay, great, sure.
It doesn't let me log in with the other computer.
Let me see if you're...
Let me try again.
So Nadia, I've also made you co-host, so
Thank you.
Shouldn't affect anything, but...
Okay. The meeting is for authorized attendees. I need to sign in. I need a username and a password. I don't think I have any.
I'll send you an email with the...
I have the password somewhere. You know what? Doesn't matter. Doesn't matter. You see the screen right? You don't see the presenter view now.
Nope.
Okay, so I'll be right back.
Okay. Nadia, I do see another...
Yeah, no, so it's fine now.
Okay.
You don't want to know. Don't worry.
It's okay. If you're logged in, you're logged in. It's fine. But you're set now?
I'm all set. I'm ready. I can go as soon as you tell me to go.
Okay. It is now 5:02.
Maybe I should go and get some coffee. You still have
That
time
sounds
for
great.
coffee. I'll be
Yep.
right back.
Sure. Ofer, I think I will make a short announcement first. So I'll share my screen, which should overwrite Nati's sharing, and then I'll do it just before, maybe 2 minutes before we start. Then I'll introduce you, and you can introduce Nati, and we take it from there.
Okay, great.
Okay. Are you guys back on campus, by the way?
Well, we were never really off campus. I mean, we're always allowed to go into campus, but I mean, it's encouraged to work from home. I mean, so I am at home with just a virtual background of campus, but yeah, but I do go into campus twice a week.
Okay.
So I mean, well, there may be another lockdown here now that we're in the second wave, but okay, that's we'll see. But
seems to be a universal statement.
Yeah.
Okay, so I'm going to share my screen. Okay, I'll start now, I think. So welcome everybody to the third day of Strings 2020. Coming to you from Cape Town in South Africa. And I wanted to make a quick couple of announcements just with regards to our rules of engagement. Just remind everybody to read and abide by our code of conduct on the webpage. Again, if you're going to sign into Zoom, please do use your real full name. We'd like to know who's asking questions and who we're engaging with. Questions, as usual, will be taken at the end of the talk. To ask a question, please use the raise hand feature on Zoom or chat specifically at the session chair and wait for them to call on you. As Hiroshi mentioned yesterday, it's a little difficult when the room gets very crowded to disambiguate questions intended for the speaker. So it's best if you use the raise hand feature. And note also that the raise hand feature orders questions chronologically. So the first person putting their hand up gets to ask their question first. I'd like to ask people to please just use the chat for physics questions posed to everybody or organizational questions privately to an organizer, or if you want to ask a question and you're having mic troubles or something, and you can ask it to the session chair in a private conversation. We'd love to see you, so you're welcome to keep your video on, especially when you're asking questions, but please do be mindful of your background. As usual, the main conference room will be active, but not live streaming during the breaks. So feel free to chat with each other and connect. You can join our Slack channels, and usually we have breakaway rooms at the end of the session, but because the end of the day today then leads on to the public talk, we're not going to be having breakaway rooms. Again, you're free to use the chat or to join the Slack channel where there's been many engaging discussions going on over the last 2 days. Our first session chair today is Ofer Harani of the Weizmann Institute. Ofer, over to you.
Okay, so welcome everybody to this Wednesday session of the Strings 2020 conference. I think it is Wednesday now everywhere in the world where we have people at the conference. And our first speaker of this session is Nathan Seiberg from the Institute for Advanced Study. And Nathan will give us a review of fractals for field theorists and field theory for fractons. So please.
Thank you. Can you hear me?
Yes.
Yeah, okay, at least one person. First, I think I can speak for the entire string community and thank the organizers here for putting together this fantastic conference during such an unusual and stressful environment. This is really, really highly appreciated. I also want to thank you for inviting me to speak here. Finally, I want to thank my friends and collaborators, these people. Can you see the pointer?
Can you share your screen again, Nadi? We can't see the
screen.
I
didn't share the screen. So let me start and share the screen. I have to start from scratch. Where do I search? Okay, can you see the screen now?
Yes, but not in the full screen mode.
You don't see the full screen mode?
No, now it's great.
Good. So finally this worked. And you can also see now the list of people that I would like to thank. These people listed here at the bottom. And I thank them for many discussions and fruitful collaborations. They shaped my view on the subject, and today I will share that view with you. So this talk is a review talk, and as such, the talk will have two parts. The first part of the title is more of a review. This would be fractals for field theorists or string theorists. So it's more of a review, and the second part would be more modern, where we'll try to cast the subject of fractals in the context of field theory. The first question we should address is, why should we discuss it here? This is a string conference. Why should we be talking about string theory, about fractals? And the point is that I view quantum field theory as a language of physics. It appears everywhere. It has many applications. It has been enormously productive and useful over the last several decades. And it's particularly prominent in various aspects of string theory. We have heard a lot about quantum field theory in the previous talks in this conference, and I'm sure we'll also hear a lot about it later during this conference. So quantum field theory appears to be everywhere, and we should be able to use it everywhere, except that over the past several years, and these are developments that I will review, mostly from condensed matter physics, but also from other communities that I will again review soon, new lattice systems were presented. They look quite standard and innocent, and they exhibit bizarre properties that do not seem to fit the framework of quantum field theory. So there are two logical options. One is quantum field theory just cannot describe these phenomena. We shouldn't even attempt to describe these phenomena using quantum field theory. And the second option is that quantum field theory should be extended such that it can accommodate these strange phenomena. Now, this is a very dangerous undertaking. And if we try to do that, we're really walking on very thin ice, because the logical structure of quantum field theory is very, very tight. It barely makes sense. And as such, so it does make sense, but if we try to change the rules a little bit, we are running a danger that we might find something which is totally inconsistent. So we'll have to tread very, very carefully as we try to do that. So in the coming slides, I will give a very brief description of the history of the topic of fractals, and mostly the timestamps and highlight some points. And later, I will discuss these developments over the last several years. I'll discuss them and review them in more depth. So the history of the subject is also very interesting. And it started with, I think, 2 papers. That's the fair reference. These 2 papers, one by Chamon in 2004, and the second by Ha, 2011. Notice the 7-year time difference between these 2 papers, showing that this paper had very little impact on the subject, and this was kind of the first time the impact started appearing. And I quoted here the titles of these 2 papers to show what these people were really motivated in. So the first title of Chamon's paper is Quantum Glassiness in Strongly Correlated Clean Systems, an example of topological overprotection. Ha's paper, this one, is really a paper about quantum information theory, and he talks about local stabilizer codes in 3 dimensions without string logical operators. And it's clear from the titles of these 2 papers that they were not interested in, or they were not motivated by the way we think about fractals today as being interesting phases of matter. So it took until 2015 and 2016 with these 2 papers by Vijay, Ha, and Fu. I will review these papers very soon. So only in 2015 and 2016, the significance of these models for describing phases of matter was realized. Notice the time span of 12 years from Chamon's paper till 2016. This is really a very long time. And the titles of these 2 papers show really the change in perspective, a new kind of topological quantum order. So they realize that this is a new phase of matter. In the dimensional hierarchy they talk about quasi-particles and excitations. And here they talk about fractal topological order, generalized lattice gauge theory, and duality. So that sounds more like the language that we pursue today and also in this talk. So in the subsequent years, after 2016, the floodgates were opened and many papers were written. Many more examples were found. So it turns out that these examples that appeared in the first few papers are not isolated. There are many, many examples, and including some development that I will review later of gapless models by Fractal in 2016, which were associated with very strange, funny gauge theories, first proposed by Xu, again for totally different reason in condensed matter physics. The other development I will review is in these 2 papers, Male, Shen, and Hermele, and Vijay in 2017. So before that, there were many other constructions of fractal models, but in this paper, they propose models which are based on taking 2 + 1 dimensional lattice systems and putting these on a layer in 2 + 1 dimensions, and stack the layers in the z direction. So in the z direction, we have a bunch of 2 + 1 dimensional field theories, and then we take another stack and stack them in the x direction and in the y direction, and we introduce some couplings between the stacks so that we end up with the 3 + 1 dimensional field theory. So this is thinking of the 3 + 1 dimensional theory as a stack of layers in 2 + 1 dimensions, and to connect to string constructions, this is similar but quite different than stacks of D-branes that are popular in the string community. But perhaps we can do something from the D-brane constructions to learn about this subject. During these years, there were also many other connections to many other branches of physics, including theory of elasticity. So these theories involve some tensor fields, and this is connected to the elasticity tensor. more connections to quantum information. In fact, this whole field started from quantum information theory, and of course, connection to topological quantum field theory, in the sense that these theories of Fractal look like a generalization of quantum field theory. It's kind of the next step in a logical progression. Now, I should apologize. This is a huge field with lots of papers, and I will not be able to do justice to all these developments. So I will be very brief here, and I picked only some of these highlights. So in the coming slides, I'm going to take some of these highlights from some of these points from the time frame that I described and discuss them in more detail. And first, I would like to discuss this model by Vijay Ha and Fu. It's known as the X-cube model. So this is a lattice model in 3+1 dimensions. So we start from a 3-dimensional cubic lattice, and we put a Z2 spin on every spatial link. This is a picture from the lattice, and on every link, can you see my pointer?
Yes.
Ah, good. So on every link, there is a Z2 spin, or in modern language, we say there is a qubit, or in an old-fashioned language, this is an IC spin. So we have a finite box with periodic boundary conditions, so finite number of spins. Every one of them has 2 states, and the Hilbert space is the product of these states. And then we have to pick a Hamiltonian. So these people picked a particular Hamiltonian. In the case of Ising, the spins are at the sides of the lattice, and the interaction is coupling between the 2 spins. In the case of the X-cube model, the Hamiltonian is the sum of 2 kinds of terms, sum over the lattice, sum over the cubes of the lattice, and another term, which is the sum over the sides of the lattice. So let me describe them in more detail. The first term is the cube interaction. On every one of, we pick a cube, say this one, and we go around the cube. There are 12 links. And on every link, we put the operator sigma 1 that acts in the 2-dimensional Hilbert space of that spin. So we multiply all of them around this cube, and then we sum them over the lattice. The second kind of term is associated with the sides of the lattice. So we pick a side, say this one, and we look at the XY plane. There are 4 links touching the sides, touching this side, and we multiply sigma 3 of these operators. So when we write sigma 3 here, what we mean is sigma 3 acting in the Hilbert space of this particular spin. So we multiply them together, and we'll repeat that in the 2 other directions. So we have here, this is AZ. What we wrote here is AZ, but similarly we have AX and AY. And we add all these terms together, and that's the Hamiltonian. The first thing I would like to emphasize about this Hamiltonian is that it is innocently looking. There is nothing funny about this Hamiltonian. We have a finite dimensional Hilbert space. The interactions are completely local. All spins interact only with their neighbors, or maybe nearest neighbors or next to nearest neighbors, but there are no long-range interactions. So superficially, it does not look conceptually different than the Ising model. This will end up not being the case. This is quite different than the Ising model, even though it looks so innocent. The second thing which is special about this particular Hamiltonian is that all the terms in the Hamiltonian commute with each other. So the first that all these terms commute with each other is obvious because they're constructed only out of sigma 1 and all the sigma 1s commute. The fact that these terms commute with each other is also clear because they're constructed only out of sigma 3. So they also commute with each other. What's a little bit less obvious but completely straightforward to check is that every term here from every side commutes with every term here for every cube. And we just have to go and check where these objects can touch, because only if the 2 operators act on the same spin can they fail to commute, and they all commute. And if they can all commute, we can diagonalize all of them simultaneously. So all the terms in the Hamiltonian commute, and therefore the lowest energy state is when all these terms are equal to 1. And so now we have just a counting problem. All the states are equal to 1, and we can ask how many different states are there such that all the states, all the terms in the Hamiltonian equal to 1. And the answer is this formula. So we work on the torus with periodic boundary conditions. We have Lx sites in the x direction, Ly sites in the y direction, and Lz sites in the z direction. And this is the total number of ground states of the system. This formula should be shocking. it would be shocking because of several different peculiarities of it. First of all, the number of ground states of the system depends on the number of lattice sites. Normally in the system, we have either one ground state. That's the standard situation. And if we have spontaneously broken discrete symmetry, we can have more than one ground state. And in a topological field theory, we can also have more than one ground state. But the common thing in all of them is that the number of ground states in finite volume is finite. There's a finite number of ground states in finite volume. Here, the answer is infinite. And it's infinite when we take the lattice size to infinity. And the number of ground states depends on the number of sides. So imagine we make the lattice a little bit bigger by adding another layer so that Lx goes to Lx plus 1. This is an infinitesimal change. So if you think of taking a chunk of material and we just paint it on one side. So we just put one layer of atoms. The number of ground states is multiplied by 4. So this is very surprising because it shows that even the number of ground states depends on microscopic details. The second surprising thing is that the exponent here, so the exponent here is the entropy. It's the logarithm of the number of states. This is the entropy. And the entropy is normally finite, or it could be extensive, proportional to the volume. Here it is infinite, but the infinity is proportional to the length of the system, not to the volume. It's being referred to as sub-extensive. It's extensive in the sense that it grows with the number of sites, but it's sub-extensive in the sense that it grows only linearly in the size, not linearly with the volume. Finally, if we try to take the continuum limit, and I'll be very precise what I mean by the continuum limit, we put a lattice spacing, we set the lattice spacing to 0, sending the number of sites to infinity, holding the physical size of the system fixed, Li is fixed. As we do that, the number of ground states is infinite. So if we want to find a field theory description of that, we'll have to learn to live with a system that has an infinite number of ground states. And not only is it going to be infinite, this infinity is going to depend on the values of Lx, Ly, and Lz in this peculiar way. Putting all this together, we see that the ground states reflect short distance physics. If we add another lattice of another layer of sites, we don't change much at long distances, but this affects the number of ground states, and the number of ground state grows as we do that. This is the hallmark of UVIR mixing. We are used to UVIR mixing in the context of a theory of gravity. In the theory without gravity, UVIR mixing occurs. UVIR mixing occurs in non-commutative field theories. And here we have another theory which exhibits this peculiar UVIR mixing. The long distance physics depends on the details at short distances. A few more details about the peculiarities of the model. The spectrum is gapped, so we talked about the ground states, and then there's a gap. And it has very strange conserved charges. In the quantum information theory, they're called logical operators. They act on the space of ground states. So logical operators are operators that commute with the Hamiltonian and act in the space of ground states. In physics language, if it commutes with the Hamiltonian, we say it's a conserved charge. And if it's act in the space of ground state, we say that this is a symmetry that in the infinite volume limit is going to be spontaneously broken. So in any event, we have a very large number of conserved charges. And the conserved charges do not act on all of space simultaneously, but they act only on the xy plane at fixed value of z. And then there's another conserved charge acting on the xy plane at another value of z, and yet at another value of z. So at every position, we have a separate subsystem symmetry. So we have an infinite symmetry group, but it's a global symmetry. The next interesting fact about this model is that there are no local operators acting on the space of ground states. So every local operator in the theory, there are lots of local operators we can construct out of these spins. If we act on the ground state, we find an excited state. It does not act within the low energy states. This is extremely significant because it means the system is robust. If we take the short distance Hamiltonian and we perturb it a little bit, then this would be described at low energies by slightly perturbing the low energy system. But the low energy system doesn't have any local operators acting there. So therefore, as long as the deformation at short distances is small enough, the long distance behavior is robust and stable. This means that we don't really have to start with precisely the Hamiltonian that was written before. In the neighborhood of in the space of couplings, the answers remain the same. The excitations are also very strange. They have restricted mobility. So the first kind of excitation are fractals. These are particles, particle-like excitations, but they are stuck at the point and they cannot move. No matter how much energy you give them, you cannot move them from one point to another. They're not created by local operators. If you could create it with a local operator, you could act with a local operator to annihilate the fractal, the state at one position, and create it elsewhere. But these particles are not created by local operators. Instead, they are created by operators that look like a rectangle, or membrane operators, and then they are created at the four sides, you don't see, at the four corners of the rectangle. So we can act with a rectangle, and it creates four excitations at the four corners. This means that even though the fractal cannot move, the operator of the fractal cannot move, we can annihilate the fractal at the expense of creating three other fractals elsewhere. It's very strange behavior. There are also particles called line-ons, and they are fixed to move on the lines, either the X or the Y or the Z direction, but they're not allowed to move diagonally. And they are planons that are fixed to be on the plane, either the XY plane or the YZ plane or the XZ plane. And these are really dipoles of these fractals. So all these things are not something that we postulate from outside. They follow from that innocent-looking Hamiltonian. So we started with an innocent-looking Hamiltonian. It turned out to be solvable, and all these peculiar features follow. Next, I would like to review Haas code. Haas code came earlier, but it's even more bizarre than the X-cube model that I have just described. Here we have two qubits at every site. And there are two kinds of interaction terms in the Hamiltonian. It's again sum of the cubes. At every corner of the cube, we have two qubits, two spins. And when we write 1 sigma 1 here, we mean 1 acting on the first qubit and sigma 1 acting on the second qubit. And we multiply this product of sigma 1s on one cube, and then we add to it the product of sigma 3s on the same cube, and then we sum over the lattice. And again, this is an innocent-looking Hamiltonian, only spins, Z2 spins, and local interactions. Nothing looks strange here. And it again has this property that all the terms in the Hamiltonian commute. And here, the bizarre features are even more bizarre than in the X-cube model. I'm only going to mention one of them, and that's the number of ground states. The number of ground states is still 2 to a power that depends on the number of sites in the lattice, Lx and Ly and Lz. But the function k that appears here in the exponent, if you wish, the entropy, is a complicated number theoretic function of Lx, Ly, and Lz. It's much more in the X-cube model, it's linear, but here it's more complicated, and you can hop around. Even if all of them are equal, so we take all the sides equal, so it's a function of one integer, even that is a very complicated function, and even that can hop around. It hop around in the sense that it's not monotonic in L. So before, when we add another layer of sites, the number of ground states grew. In this system, it can go up, it can go down. It's bounded by a term roughly proportional to L, but it can go down to a finite number and then go up again. So in this case, we can find sequences of size of the system as L goes to infinity with finite limit for K of L, or we can find sequences where K of L diverges as in the X-cube model. So this really raises the question, what is the limit as L going to infinity? In the X-cube model, it was infinite and said, well, we'll have to learn to live with it. And now there isn't even a well-defined limit. Depending on how we take the limit, we get a different answer. And we could ask, is there a continuum limit at all? The next kind of model that I would like to discuss was introduced by Fractal. And these models are gapless. So the previous two examples I mentioned are gapped. These are gapless models. And he was motivated by a very strange gauge theory that was described, introduced by Shu for totally different reasons. Here we have a gauge theory where the time component of the gauge field A0 is standard gauge transformation node. It's shifted by D0 alpha. But the spatial components are not a vector that carries one index, but it's a tensor that carries two symmetric indices. Very much like gravity, but it should not be confused by gravity. This is not a theory of gravity. So the gauge transformations are as spelled out here. A0 is shifted by D0 alpha, and Aij is shifted by Dij alpha. And then we can form gauge invariant combinations, electric field and magnetic field, which are certain tensors in the indices. And you can check that under this gauge transformation, this E and this B are invariant. And we can write a Lagrangian, which is roughly E squared minus B squared. And we can analyze the spectrum. And this theory has gaseous photons. So the photons, which are the plane wave solutions of this system, and they exist. Now, what Pratt could notice is that this gauge theory has an interesting property. These are the gauge transformation laws. In Gauss' law, which is normally one derivative on E, which has one index, here Gauss' law involves two derivatives acting on E with two indices, and that's the charge density rule. So if we add matter fields, charge matter fields to this system, this is the form of Gauss' law. And as a result, both the charge and the dipole charge are conserved. To see that, we substitute this double derivative term in here, and then we can integrate by parts. And because we have two derivatives here rather than one derivative as in the ordinary case, we can also integrate here by parts. And as we integrate by parts, we see that the total charge and the total dipole charge depend only on what's going on at infinity, and therefore they are conserved. So as a result, Pretko realized that the charge excitations of this system have restricted mobility. They are constrained both by charge conservation and dipole conservation, and they are fractals. I'd like to present a slightly different interpretation, equivalent but different interpretation of this statement that will be easier to generalize. The discussion here works on non-compact space. So we check the electric field at infinity, and we talk about charge conservation. After all, charge here is the gauge charge. So I think it's better to think of the theory without matter fields and represent the matter fields as defects. So we think of probe particles in the theory without dynamical matter fields, and that theory has defects. And the defects are represented by Wilson lines. So of course, if we look at Gauss' law in the presence of the Wilson line, we're going to get a delta function at the location of the defect, and that would be the charge density that appears here, except that it's classical. But here comes the crucial point. In a normal theory, this defect in the time direction can bend in space by using the existing AI, by introducing the vector, using the vector potential. In our theory, there's no AI. And since there's no AI, the defect cannot bend. And as a result, this particle cannot move from one place to another. So this is kind of another interpretation of this fact, which works also in finite volume, so we don't need the charge at infinity. The last development I would like to review in my historical part of the talk is the couple layer construction. I mentioned it briefly earlier when I presented the timeline of the historical developments. It was done in these two papers. In these two papers, they studied 2+1 dimensional lattice systems on a layer, and saying the XY plane, and then they stack these layers along the Z direction. So far, the different layers are completely decoupled from each other. So 3+1 dimensional space is constructed out of a stack of 2+1 dimensional layers. And then you can repeat that in the two orthogonal directions. So this is the XY direction, you can repeat it in XZ and in the YZ directions. And then add some coupling between the stacks. We'll soon discuss why this is a good thing to do. I want to mention two more modern developments. One is by these authors who said that such a stack construction can be taken to curved space. So far, the models were in flat T3, but these authors suggested that such a stack construction can be taken to a curved space, provided the manifold, the space manifold, is foliated, and the leaves of the foliation, these layers are along the leaves of the foliation. And more modern development was based on putting the continuum theory on the layer, not a lattice model, but a continuum field theory, continuum topological field theory on each layer, and couple these TQFTs in the stack in one direction, in the other direction, and in the third direction. So why is this a good thing to do? Some properties of the fractal models become manifest and intuitive. The first fact is the restricted mobility. So we're going to have excitation that are stuck on one layer. They cannot move from one layer to another, nor can they move along the other. So they can move, they're stuck in these layers and they cannot move in this direction. And then there will be similar ones that are stuck on the orthogonal layer. So that's the first thing that is nice about it. We can also have excitations that are stuck in the location where two layers intersect each other. So the XY and the XZ. So these would be excitation that can only move along one line, the X direction. And finally, those that are restricted to be at a position where the three orthogonal layers, all three of them touch at the same point. So these would be the fractal. Second, I mentioned the subsystem global symmetry. In this case, they can be interpreted as a symmetry that acts only on one layer, but not at the other. So that gives a nice interpretation of why we have this subsystem global symmetry. It also gives an intuitive picture for the sub-extensive ground state they cannot see. So imagine we put a field theory which has 4 ground states on each layer. So this is a torus and this is a Z2H theory. It has 4 ground states. Then the number of ground states will be 4 to the power of the number of layers. And if we also add a stack in the other directions, we can just multiply all these numbers and we roughly get the answer that is obtained earlier. So thinking of 3-dimensional space as decoupled field theories or almost decoupled field theories on these layers explains all these facts. The crucial aspect is that it makes clear why the observables are discontinuous. Because the charge on one layer has nothing to do with the value of the charge in another layer. And observables in one layer have nothing to do with the observables in the other layer. This thing really means that taking another continuum limit, as we take all these layers together, is going to be challenging. In other words, this theory can perhaps be made sensible as a continuum field theory on each layer. But if we try to take the number of layers to infinity and have a genuine 3 + 1 dimensional continuum field theory, we'll have to take the number of layers to infinity. And then at the limit, as the spacing between the layers goes to 0, is going to be challenging. Finally, it's not yet clear whether all fractal models can be given such a coupled layer construction. So I'd like to summarize with a set of questions that these developments raise. I think that every one of them is interesting. The first question is, are there more examples? And more interesting, perhaps them examples with more exotic phenomena. These phenomena are quite exotic, we're not used to them. We should look for more examples, and condensed matter people are producing papers, finding more and more examples of these phenomena. The second question is, what are the underlying reasons for the bizarre behavior? The Hamiltonians we started with look quite innocent, and yet they exhibit this strange phenomena. If we started with another Hamiltonian, it might or might not present this bizarre behavior. How can we tell from the start that we're going to end up with such a phase? That's from the short distance point of view. From the long distance point of view, we would like to understand what are the allowed phases, we would like some kind of an organization or classification of the allowed behavior. What kind of exotic phenomena are there, and how should we classify them? Normally, when we have phases, the way we think about them is we use continuum quantum field theory to describe them. We have a complicated system at short distances, and at long distances, we say it is captured or is described by a continuum quantum field theory. That's what we normally do. So we would really like to know whether these systems can be described by a continuum quantum field theory that will capture the long distance behavior. It will capture the long distance behavior in a universal way. Namely, it will be independent of all the details of the microscopic physics. And we would also like to formulate the theory on more non-trivial manifolds and make sure that these theories really follow all the standard rules of quantum field theory. And I can go on and list many more questions that can be raised. So we would like to look for a low energy continuum field theory, and also review again why. Now, the properties of the models, as I've just summarized, and in particular the mixing between the UV and the IR, make this thing almost impossible. It seems to be against the spirit of the renormalization group picture, where physics at long distances is independent of details at short distances. And here I emphasize more than once that we have this UV-IR mixing. Phenomena at the lattice scale affect the behavior at long distances. So if we want to do that and really find a continuum field theory description of these phenomena, we need to extend slightly the framework of quantum field theory. And I emphasized before that this is a very dangerous thing to do, because quantum field theory manages to be, it's rather miraculous that it manages to be consistent, but if we start making changes in foundational things, we might wreck the whole intellectual structure. So we should be extremely careful. And we have two motivations for doing that. One is for fractal theory. We would like to have a universal description of these systems, a way to organize the different phases by focusing only on the things that are interesting and relevant at long distances. And the second motivation is in the other direction. If we do extend the framework of quantum field theory, maybe this will teach us something new about quantum field theory. So making progress along any of these two routes, I think, would be a useful thing to do. So this brings me to the starting point of the work I've been doing with Shu and Shao. And we tried to do exactly that. So we tried to follow these existing lattice models and to give them a continuum quantum field theory description. And of course, we had to break the rules a little bit. And I claim that every rule we broke was essentially unavoidable. We didn't have a choice. So perhaps finding a continuum field theory description of these systems is totally misguided and we shouldn't waste our time. But if something like this happens, we will really necessarily we'll have to break these rules. So what are the new elements? The first element is space-time symmetries. If we want a continuum theory, we should have translation symmetry. And we should certainly not have Lorentz invariance, that's clear, but we are also not going to have rotation symmetry. We're going to preserve only the subgroup of the rotation group SO3, which is invariant under 90-degree rotations. So we're only going to have rotation under 90 degrees. That would be the symmetry group. That is not shocking, and it's easy to write quantum field theories that are invariant only under this group. In fact, we do it all the time. The second element is also not that shocking. We're going to impose this exotic global symmetry in gauge. This is a little bit less standard, but it's not too scary. And I'll show an example of this before. In fact, I mentioned already this gauge theory with the symmetric tensor earlier, and I mentioned some of these subsystem symmetries. Perhaps the most dramatic thing we do is to allow discontinuous fields. Now, normally in continuum field theory, space is taken to be continuous. Space is taken to be continuous, and we have maps from continuous space to a continuous target space. And what we're going to do here is keep space continuous, because that's what we want to do, but the target space, we will allow some discontinuities in the space of functions. Now, on a lattice, everything is discontinuous, and the value of the field at one side is totally unrelated to the value of the field at another side. So our fields will be more continuous than that, but on the other hand, some discontinuities will be allowed. Now, if we allow discontinuous field configurations, and we study gauge theories, the gauge parameters, and correspondingly also the transition functions, will also have to be discontinuous. So we see that we open here a Pandora box. There will be all sorts of singularities, and we'll have to learn how to deal with these singularities. And we insisted that whatever we do will make sense and will be independent of the details of the lattice. So let me describe the first model of this kind, the tensor gauge theory. I already discussed it before, but a variant of this theory was first introduced by Shu and Wu, again for different reasons, and it was called hollow tensor gauge theory by these authors. So in the symmetric tensor theory, Aij is two indices, two symmetric indices, so it's a 3x3 symmetric matrix. If we impose that I is not equal to j, we remove the diagonal elements, and hence the name hollow tensor gauge theory. It's not invariant under SO3 because removing the diagonal elements is not a statement that it's invariant under SO3, but it is invariant under the cubic group, which is S4. So the gauge transformations are, as I wrote before, A0 is the standard gauge transformations, and Aij is, there are three of them, symmetric tensors with unequal indices. It's not a vector representation, so we denote the representation as 3'. And again, we have the electric and the magnetic gauge fields, exactly as before. And there are some funny representations of the cubic group. And these authors noticed that this model is actually unstable in the following sense. It's well known that 2 + 1 dimensional ordinary U1 gauge theory can be described in the continuum, but if we think of it on the lattice, it's unstable because on the lattice we have monopole operators, and on the lattice there's no monopole magnetic symmetry. So as we go to long distances, we find this U1 gauge theory, but then we can have monopole operators in the Lagrangian. This is known as Polyakov mechanism. And what they do is destabilize the model. So 2 + 1 dimensional QED or U1 gauge theory is not stable because of monopole operators. But in the continuum, we can study it. In fact, I'm still going to argue that the statement I made here is imprecise. So in the continuum, we can study it. So let's study it in the continuum. So we put this theory in the continuum, and we want to ask, what's the spectrum? Well, that's a straightforward exercise in quantum field theory 101. We put a plane wave, we substitute it in the solution, and we find it in the Lagrangian, and we find the dispersion relation. So this is the dispersion relation. Omega is the frequency, and kx, ky, and kz are the momenta in the space directions. If we look at the spectrum, we have two gapless modes. Let's do the counting. In A0 = 0 gauge, there are 3 degrees of freedom in Aij. We have to subtract 1 because of Gauss' law, and we have 2 propagating polarizations. Okay, that looks, the dispersion relation is non-standard, but these are 2 particles, 2 massless particles with funny dispersion relation. What's more interesting is if we limit ourselves to the special modes where kx and ky both vanish. So let's see what happens. This term is 0 because kx and ky vanish. This is 0 because kx is 0. And this is 0 because ky is 0. So that this last term is absent. And as a result, we can have omega = 0. So if we take kx = ky and set them to 0, no matter how large kz is, we have 0 frequency. And of course, the same thing is true in the other directions. This is quite surprising and quite unusual, because it means that we really have this UVIR mixing that we talked about. This dispersion relation tells us that we have infinitely number of modes labeled by kz at 0 frequency. At 0 frequency, we have an infinite number of modes with momentum in the z direction arbitrarily high, sensitive to what happens at very high momentum. So this is the key to the peculiarities of these system models. In fact, these models with omega = 0 need to be quantized a little bit more carefully. And in this particular case, they are actually not lifted and they stay at zero energy. This is not completely obvious because in variance of this system, these modes actually acquire a large energy. So we end up with a very large ground state degeneracy. Notice how similar it is to what we're trying to achieve. We end up with a very large ground state degeneracy and with UVIR mixing from what appears like a rather innocent looking continuum field theory, and I underscore the continuum. Now, when I see a field theory, the first thing I try to do is dualize it. Maybe this will teach us something. So we can dualize it, and we can dualize it to a theory with another field, phi hat, which is not a gauge field. So all the subtleties with gauge symmetry are gone, and this field is gauge invariant. I don't call it a scalar field because it's in the 2-dimensional representation of this cubic group. And the dictionary between the gauge theory variables and these non-gauge theory variables are written here. The electric field is the spatial derivative of phi hat, and the magnetic field is the time derivative of phi hat. Again, this is very similar to U1 gauge theory in 2+1 dimensions, where the gauge fields is dual to a compact scalar. The formulas are essentially the same. The differences are that A, we are in 3+1 dimensions rather than in 2+1 dimensions, and the gauge theory has these funny indices rather than an ordinary gauge theory, and the scalar of 2+1 dimensions becomes this phi hat in some non-trivial representation of the rotation. So the two gapless modes that we found before now get a new interpretation. They are simply the two modes of phi hat. So that's not surprising. The duality works. And the ground state degeneracy follows from winding modes of phi hat. This is again similar to what we know in 2+1 dimension, with the winding modes of the scalar represent these charge states. And the dangerous monopole operator is e to the I phi hat. So in 2+1 dimensions, the same thing is true. We can dualize the gauge field. We have a compact scalar. The monopole operator is e to the I phi. And on the lattice, it is there and it destabilizes the system. But in the continuum, we can tune it to 0. In this case, there's actually a surprise. If we look at the long distance physics, this operator is actually a very high dimension. And since it is a very high dimension, unlike the 2+1 dimension of ordinary U1 gauge theory, this system is actually robust. So it is not gapped as in ordinary U1 gauge theory. Let's discuss the gauge transformations in a little bit more detail because there's a surprise here. So the gauge parameter was alpha, and A0 goes with D0 alpha, and Aij goes with Di Dj alpha. And alpha is compact, so it's a circle value field. It's a circle value parameter. Alpha is identified with alpha plus 2 pi. And in a normal gauge theory, alpha can be continuous. But in our case, we also allow certain discontinuities. So we allow certain discontinuities, and the bulk of the work was to justify which discontinuities are allowed and to motivate them by a careful analysis of the continuum limit of the lattice. So we started from a lattice, and we very carefully took the continuum limit, and that told us what kind of discontinuities we should allow in the continuum limit. And this is a typical large gauge transformation. It's not continuous. It jumps both at y equals y0 and at x equals x0. But you can check that it is periodic on our space. If x has length nx and y has length ny, then this formula jumps as we shift x by nx or y by ny, but the jump is by 2 pi times an integer. This theta is the Heaviside theta function, so it's either 0 or 1. So this is a good gauge transformation to study, and with such gauge transformations, fluxes are quantized. So what did we do with it? We have these discontinuous gauge parameters and perhaps similar field strength, and one might get very nervous. Maybe what we're doing is totally misguided. So I want to emphasize that the rules we have are unambiguous. They reproduce the lattice answers, and they're universal in the sense that if we modify the lattice action by a small amount, then the answers in the continuum do not change. Finally, in the paper to appear, we reproduce all this structure, including the discontinuities, by a couple layer construction of ordinary U1 gauge theory in 2+1 dimensions with a funny scaling. So that makes us more clear that what we're doing is sensible. So we discussed the U1 gauge theory. Let us discuss the Zn gauge theory. How do we go from a U1 to Zn? Well, if we have a U1 gauge theory, we go to Un by Higgsing it. So we introduce a Stuckelberg field phi. So A0 and Aij are U1 gauge fields as before with the funny transformation law. And phi is the Stuckelberg field with charge n. This is the n that appears here. And this is the gauge transformation of phi. And this Lagrangian gives us a description of the continuum theory. So let me guide you through that. This combination here is gauge invariant, and this combination here is gauge invariant. I should emphasize that this is a standard way to Higgs a U1 gauge theory. We just add such a Stuckelberg field. The only novelty is that we have two derivatives here and two derivatives here. Other than that, it's the standard construction. B and E are Lagrange multipliers. They set this combination to 0 and this combination to 0, thus fixing the system. I would like to mention in passing that the scalar field phi can be dualized to another funny gauge field, A hat. And normally when we do that and we have this phi here, say plus 1 dimension, we find a BF description of the ZN gauge theory. And therefore we can rewrite this system using a BF description where the F is the field strength, this magnetic field and electric field. And what's normally called B, here we call it A hat, is this new gauge field which is dual to the scalar field phi. And the coefficient n here, which determines the gauge loop, which will be Zn, so n here is determined by the coefficient here and here. And it's the same as the coefficient here in front of the action. This is determined by the same large gauge transformation that I discussed before. What are the defects in the system? So it's very similar to what we discussed in the U1 theory earlier. The simplest defect is a particle at a point. It sits at a point and it cannot move in space. It is a fractal. And since we don't have AI, its wall line cannot bend. So this is a fractal. The second kind of defect we can have is take two of them, one with charge 1 and one with charge -1, and separate them in the x direction. So if we ignore for a minute these two terms, we have an integral dx here, and divide the x here, so we can integrate by parts. And that gives us an object like this with coefficient 1 at x2, and another one with coefficient -1 at x1, and that tells us that what we have is a dipole. This object by itself cannot bend, and therefore the fractal cannot move in other directions. But in this case, it can, because we don't have AX or AY or AZ, but we do have AXY, and AXZ. So this combination is gauge invariant. Namely, the dipole of these two particles with charge 1 and -1 can move in the Y and Z direction. So we separate them in X, and they can move in Y and Z, but not in X. So this is a planar. So we see here that the restricted mobility follows from the gauge symmetry. There are also other defects coming from winding operators of phi, or equivalently from the Wilson lines of A hat. And the nth power of these defects is trivial, because it's a Zn gauge theory. Let's work out the spectrum of the system. This is our Lagrangian, I described it before, where E and B are Lagrange multipliers. The Lagrange multipliers set this combination to 0 and this combination to 0. So we can solve for A0 and solve for Aij. This is the solution. So for every configuration of phi, we got rid of B and E by integrating over them, and we solve for A0 and Aij. So the entire dynamics is captured now only by the space of configurations of phi, and we need to mod out by gauge transformations. So the ground states are the space of phi's modded out by these gauge transformations, and they're generated by the same large gauge transformation that I discussed before. I would like to remind you that when you study an ordinary Zn gauge theory, you do exactly the same thing, and the way you count the ground states is by doing exactly this manipulation, except that you study continuous functions here. So there are various winding modes. And here we allow also the discontinuous winding modes. So what does it mean? If we put a coefficient n out front here, then we can cancel it by gauge transformation. So we shouldn't do that. This means that for every value of x0 and for every value of y0, where we allow these discontinuities, we have an integer modulo of n. So these are the spatial ground states. And if we add also the other direction, this is in the xy plane, we can do it also in the other planes. So if we account for the other directions, and we account for the zero mode, the common zero mode, which needs to be treated more carefully, and we temporarily put it on the lattice, we end up with this number of states. And this formula should be familiar because we saw earlier a similar phenomenon, a similar formula earlier in the talk. So let me skip some discussion of the properties of this model and just say that this is nothing but the continuum field theory description of the Zn version of the X-cube model. So by doing that, we constructed the continuum field theory of this X cube model. And the price we pay is a small price by using these funny gauge fields in fields that are not SO3 invariant, but only in representations of the cubic group. But the more dramatic price we pay is allowing these discontinuous gauge transformations. I'd like to compare this situation with a familiar example of an ordinary ZN gauge theory in 2+1 dimension, an example that many of you have already studied in a lot of detail from many perspectives. So I summarize it in a table here. And let me start by this column, ordinary 2+1 dimensional ZN gauge theory. It can either be given an intrinsic description as a ZN gauge theory, or as a U1 gauge theory, X down to Zn. It also has a BF description, where in terms of U1 times U1 gauge theory with off-diagonal coupling with the coefficient n in the action. The phase of the system is gapped. There are no excitations. The continuum field theory has no excitations. They're only the topological degrees of freedom. And it's robust in the sense that there are no local operators that can destabilize it. The defects and the operators of the system are Wilson lines of A or Wilson lines of A hat, the other gauge field. In terms of the Zn gauge theory, they can be thought of as electric and magnetic lines. And what they describe is the motion of probe particles. There are no particles in the topological field theory. The motion of probe particles, and these particles are anyons because they can have non-trivial braiding between them. And if we formulate the theory on the lattice, there are n squared states on the lattice corresponding to the winding in one direction or in the other direction, or corresponding to the Wilson lines of A in A hat along one of the cycles. Let's contrast that with the situation of our tensor theory. So first of all, we are in 3+1 dimensions rather than 2+1. And it's not an ordinary gauge theory, but a tensor gauge theory. But other than that, this detail, they're very similar. So we can either give it an intrinsic description as a Zn, or as we did here, U1 X down to Zn. Or we can dualize the field and give a BF description like we wrote here, with the information in which value n it has appears in front of the Lagrangian as a coefficient, very similar to what we have here. The phase is gapped as here. There are no excitation. This field theory is not topological, but this field theory has no particles. It describes only the zero energy states. And it's robust in the sense that it does not have any local operators acting in the space of ground states. The observables of the theory are Wilson lines and strips of A and A hat. And they have interesting algebra. They don't commute, and the ground states are in some representations of this algebra, very much like what happens here. And they describe the world lines of probe particles, but these probe particles are not just anyons, they are these fractals, linons, and planons. And the number of ground states is also interesting. Here we have n square states on the torus, independent of the number of lattice sites. In fact, there's no lattice in this story. Here, the number of states on the torus depends on, is infinite in the continuum limit. And if we regularize it, it is subextensive. It's term linear in Lx, a term linear in Ly, and a term linear in Lz. So you see the situation is kind of similar. And the situation is kind of similar. And in fact, this theory can be constructed as a couple layer construction made out of layers with this Zn gauge theory. So explaining why it is similar, it also shows in what sense this column generalizes the behavior that we see here. This is kind of the next step.
In 95 minutes.
Let me summarize. Does this answer your question? So let me summarize. In the first part of the talk, I gave an overview of the history. And the punchline was that fractals exhibit interesting properties, and they fall into two classes. One is this bizarre UVIR mixing. We have a large ground state degeneracy. Number of states of the ground states grows exponentially with the length of the system. It's not with the volume, but with the length. And sometimes, this is particular in Haas code, there isn't even a well-defined limit as L goes to infinity. So it's not just that it's infinite, we get a different answer depending on how we take L to infinity. And the observables are discontinuous. So if we make L very large and the lattice is very fine, we move the observables from point to point and they have totally unrelated values at different points in space. So this is this UVIR mixing that even the low energy physics is sensitive to some extent to what happens at high energies. The second peculiar thing is these excitations with restricted mobility. The restricted mobility these are particles that are stuck at one point, or can move along a line, or can move on a plane. Now, all these behavior, funny as it is, seems incompatible with the framework of continuum quantum field theory. I think this is clear. It is interesting for many other reasons independent of the connection to continuum quantum field theory. And although, as far as I know, there is no material in the lab that exhibits these properties, given that the Hamiltonian looks so innocent, there is really no obstacle to having such a material in the lab. And in fact, people look for it and even have some ideas how to use it to have technological applications or technological applications of these systems once they are found. So this was the first part of the talk. In the second part of the talk, presented a non-standard continuum quantum field theory. And it was non-standard in three ways. The first, it was invariant only under discrete rotation, only under 90-degree rotations. And I glossed over a lot of details here. There's really a lot of fun group theory there that is connected to the fact that the group is discrete. Second is the exotic global and gauge symmetries. This was the funny gauge symmetry. First, the global symmetry was the subsystem symmetry, and the funny gauge symmetry was this object with symmetric indices. This was the most dramatic thing, that the fields and the gauge transformation parameters can be discontinuous and even singular. Here is where we really were very careful, because the bulk of the work was getting this thing straight. And we found what I believe is a consistent set of rules about what we are doing. And we made sure that not only is it consistent, it agrees with what appears on the lattice. These fields are more continuous than on the lattice. So we did not allow discontinuities which are as bad as on the lattice. But on the other hand, they are less continuous than, or more discontinuous than in standard continuum field theory, because we are, as you saw before, we allow things to jump. And the nice thing is that these continuum field theories capture all the universal properties of the lattice models, and they reproduce the long distance physics and the properties of core particles. That's what they were designed to do. And as a question of outlook, there are many things we don't understand. We'd like to make the treatment of the discontinuous field more precise. Even though we were careful, it's quite clear that this should be stated much, much better than we did. We also have these funny gauge fields with these funny bundles twisted by these discontinuous transition functions. Again, it's quite clear to me that this should be stated much better. I'm quite sure that this is not the last to be said about this subject. We'd like to put these theories on more complicated manifolds. Perhaps the idea of using foliated manifolds and putting the theories on leaves is in the right direction. We'd like to repeat it for other known lattice models. In fact, we are writing a paper with the co-authors I mentioned on the title page, repeating this analysis for other models that exist out there and recasting the existing literature in this new language. What I think will be more interesting is to find new such models. So as a finish, I will say thank you, and please, please, please stay healthy.
Okay, thank you very much. Okay, so I see the first question is from Edward Witten. So Edward, please.
I just wanted to ask if there's any thoughts about understanding the Ha code in a similar language.
This is an excellent question. I do not know how to set Haas code in the similar language. There are various models that are simpler than Haas code, but more complicated than the X-cube model. And they can be recast in this language by extending the kind of gauge theory that we use. Specifically, this is a paper we are writing with these people I mentioned, with Pranay, Hotat, and Shuhen. This is the model known as the checkerboard model, which is in complexity in between the X-cube model and Haas code. So this model can be recast in this framework. Haas code is more complicated for a number of reasons, and I do not yet know how to phrase it in this language. But this is very high near the end of, it's very high at the end of my, it's very high on my agenda to do Haas code.
What sort of ground state degeneracy is there in the more complicated models that you just mentioned?
So it's also as a function of the length. It's also relatively simple. It grows linearly. It does not have the erratic behavior of Haas code. The special thing about Haas code is that the log of the ground state degeneracy changes erratically with the number of sites. It goes up and down and up and down, and it's this complicated number theoretic function. But I don't think that this will really be an obstacle to include it in this language. Maybe I should mention another peculiarity of Haas code, which is kind of more local. It's not just how many. So the ground state degeneracy depends on boundary conditions, on how many sites we have. The other thing is what are the local observables? They are not things at the point, but they are lines. The lines I described here are lines along the X direction or the Y direction or the Z direction, and they become various Wilson lines of the characters in our story. In Haas code, these objects are kind of fractals, hence the name fractal. So that I think is more of a challenge because this is something that is independent of the boundary conditions, independent of how many sites we have. The erratic behavior in the number of ground states come from accommodating these lines, which are like fractals, accommodating them with the periodic boundary conditions. This is the underlying reason for the complicated formula. So what we should really focus on, I think, is not the boundary conditions in the ground state degeneracy, but on these observables, which are these lines. But I don't have an answer because I don't have a continuum theory for this.
Okay, the next question is, sorry, do you have another question, Edward?
I just said thanks.
Okay, so the next question is from Guillaume Pimentel, please.
Hi. So you mentioned this UV-IR mixing and the ground state degeneracy as a signature of that. Can you see something related to the fluctuations that reflects this UV-IR mixing?
As far as well, I'll give you two answers. Number one, the UV-IR mixing here is not the same as the UV-IR mixing in non-community field theories where they come from the fluctuation. But I'll give you also another answer, which I think is more interesting. Whether some of the phenomena here occur classically or quantum-mechanically is in the eye of the beholder. Because if you perform a duality transformation, what appears classical in one language is quantum in the other language. So for example, when I presented the counting of ground states in the ZN gauge theory, I did it using the language of fixing U1 to Zn, and then the counting of ground states appeared classically. I just counted the number of configurations. In a dual language, when we describe this as a BF system, or as U1 times U1, the counting of ground states comes from a quantum effect. That is true even without, in standard ZN gauge theory in 2+1 dimensions. The fact that there are n square states on the torus, in one description is classical, you just count how many holonomials we can have. And in the other picture, it comes from quantizing this space space. So whether something is classical or quantum can depend on your description. And this is common in duality.
Okay, thank you.
Okay, the next question is by Daniel Harlow, please.
Yeah, so in all these examples, it seems like explicit breaking of space-time symmetries is is very important. And my guess is that's really true, in which case it might be possible to, for example, prove that if you do have Lorentz invariance, this kind of behavior is impossible. Do you have any thoughts about that?
No. Well, you could say the same thing about non-commutative geometry. It's also, some of the peculiarities arise because it's not Lorentz invariant.
Well, that's what we expect, but do we actually know that it can't happen in a Lorentz invariant system? I mean, that's certainly what I expect, but I don't know of a theorem like that.
I do not know that, but I also don't, I think that the more urgent question is, well, I don't know if it's more urgent. The question I find more interesting is what are these phenomena that can or cannot fit in the Lorentz invariant theory? Are there other such phenomena that are equally strange or even more strange that can arise? The lesson for me from all that is that there's a whole zoo of interesting examples out there that are very surprising. We didn't expect them, and they are there in theories that are not that different than the theory that we know and love. And I think what we ought to do is just explore that.
Yeah.
Okay. Any further questions?
Make a comment?
Yes, please.
Regarding to space-time symmetry, there is the so-called Carroll symmetry that is a contraction of the Lorentz symmetry we see going to infinity, such that the particles invariant under that symmetry does not move. I am wondering if there is any sort of connection with these fractal theories where you have restrict mobility.
Yes, so it's an excellent question. And in fact, I like to think of all of these developments as a Rorschach test. You know, this test in psychology that you get these ink figures and you see what you like in them. So I gave a talk at Harvard, and after the talk, Gabadazzi came to me and said, these funny symmetries are like Galileo's. And of course he was right, they were just like Galileo's. And then Qumran sent me an email and said, the same kind of behavior occurs also in topological field theory, topological string theory, occurs in topological string theory. And he sent me a reference, and of course he was completely right, the same behavior is there. And then Jaume Gomez asked me the same question that you asked me about, you know, it's the same as the Carroll symmetry. And I looked it up and yep, it's very similar. So I view that as good news. This is not so crazy. You know, we have already seen similar things elsewhere, and we should use all the technology we know we can use from the other applications of that to help here. So far, I haven't succeeded to make any use of that.
Okay, thank you.
Okay, the next question is by Rajesh Kupakumar, please.
Hi, hi, Nanti. This is more about the lattice formulation. So the question is, you mentioned these Hamiltonians at the beginning, which are very innocent looking. So I was wondering, is there some criterion by which we might know which microscopic lattice Hamiltonians, without computing the ground state degeneracy, which shows these exotic behaviors, but without in some way estimating the ground state degeneracy, but just by looking at the structure of the Hamiltonians, is there a way to sort of figure out which of these could have these exotic properties?
So the answer is a priori no, and in fact, this is exactly what I said here when I raised this point. I asked exactly this question. We look at this system, how do we know why the Ising model doesn't do that? Or is this thing that does not look that different does do it? And I don't know an a priori way. I think that it would be nice to have such a thing, but I don't know.
Okay, thanks.
Okay, the next question is from Juan Maldacena, please.
In the case that you have gapless modes, how stable is the structure under the addition of higher derivative terms in the Lagrangian? I'm worried about those discontinuous field configurations you mentioned.
So the discontinuous field in the example that I mentioned here, the massless modes that we had are stable against higher derivative terms as long as we preserve the global symmetry of the system. So the system has a global symmetry, and the large degeneracy of ground states is actually guaranteed as a result of the representation of the symmetry of that model. So this model has an electric global symmetry, and acting on the global by the electric global symmetry takes it from one of these modes to the other.
Okay, thank you.
Okay, I see no further questions, so let's thank Nati again. Oh, the next talk was originally scheduled to be in 45 minutes, but the schedule was modified, so the next talk will already be in 15 minutes, the talk by Ibrahim Abba. So we'll have a 15-minute break now, and we'll continue in 15 minutes.
Hi, Ibu. Do you want to set up and just check that your presentation and screen sharing works? Hi, Ibu.
Hello.
Hi, great. Excellent.
Can you hear me fine?
Yes.
Very good.
Okay, you're all set, I think.
Okay, so we'll start in 2 minutes.
Hello.
Okay, are you
Good.
ready to go? Okay,
Thank
very
you.
well. So our second speaker of this Wednesday session will be Ibrahim Abba from Johns Hopkins University, and he will tell us about anomalies of superconformal field theories and geometric engineering in M-Theory. Please.
Thank you for the, thank you to Jeff and the organizers for inviting me. It is an absolute privilege to be speaking at this conference, and it has been quite successful. And I should say that as being born and growing up in Senegal in West Africa and studying physics in the US, it is a special privilege for me to speak at this conference, the first strings conference in Africa. So to start, I will tell you about some work that I've been doing in the last few years with a couple of quite excellent postdocs, Federico Bonetti and Emily Nardoni, and also my upcoming students, Peter Wecht and Ruben Minazian, who is at Saclay. So the general, so there are some papers and there's more to appear. So general landscape of problems that I will wish to think about is geometric engineering of QFTs from string theory. So this has been a sort of hallmark to study QFTs from string theory, and it's really been one of the true success of the framework. So historically, of course, we've done a lot of this using brain systems. Recently, however, we've discovered that we can do geometric engineering by actually not so much as starting from string theory, but taking quantum field theories and partially compactifying them on various manifolds, such as to get some lower dimensional quantum field theory. This has the advantage that lower D QFTs can be defined and studied by using some internal geometries. Typically, such systems are strongly coupled, and this sort of a program exploded about 10 years ago with the starting work of Gaeta and Gaeta-Mornetsky. One of the nice things about this program is many of these CFTs admit arbitrary flavor symmetry. The examples are 6D compactification on Riemann surface. So one of the things we would like to understand is how to get physical observable data from the geometric definition of these CFTs themselves. And in that light, the most basic question you can sort of ask and try to understand is what are the 't Hooft anomalies of CFTs from the geometric setup itself. So to briefly review basic aspects of 't Hooft anomalies that we are familiar, we think of them as sort of gauge anomalies for global symmetries. This could be Poincare, flavor, discrete, or some of the more recent understood higher form symmetries. In general, we can understand them by comparing partition functions as a function of background field valued in a specific global symmetry. Since such a background field are not integrated over, the partition function can transform non-trivially. And when it does, this can have an opportunity for there to be a quantum anomaly where the quantum symmetry, where the partition function is not a sort of a scalar under such a symmetry. We say a 't Hooft anomaly exists if we can't remove such a phase by a counter term, and also more importantly, when it vanishes when we turn off the background field. There are many reasons why we love 't Hooft anomalies owed to their non-renormalizability conditions. For the sake of geometric engineering and in the study of non-Lagrangian theory, they have an even more privileged position in that they can be used as a proxy to measure degrees of freedom and in some way as a proxy for Lagrangian data itself. So the way we characterize anomalies is through what's typically called, is through the anomaly polynomial. In this talk, I will worry mostly about continuous symmetries. Later, I will say some aspects of discrete symmetry. And the phases that we introduced last time, they appear by looking at variations of effective partition functions, and the anomaly can typically be written as an integral of some local density. Such local density can be characterized in the case of continuous symmetries in terms of an object that lives in 2 dimensions higher, which we call anomaly polynomial, which itself is a polynomial in the curvatures of the background fields that we can turn on to study these global symmetries. The canonical example is to consider, for example, 4D series, where you would have a 6th polynomial in terms of background fields, F, and the coefficients are typically the perturbative anomaly that we would compute in introduction quantum theory class from triangle diagrams. So one thing we can do with the anomaly polynomial when we in geometric engineering is you can integrate them down when you have a lower DCFT from a higher DCFT. And when you do that, this is just anomaly matching across dimensions. This has been a sort of successful approach to studying anomalies of various CFTs in F-theory, in M-theory, in type 2B, and even more recently in aspects of trying to understand black hole physics and microstate counting. However, the procedure of just integrating down an anomaly polynomial of a QFT can miss accidental symmetries, can miss new degrees of freedom that can appear due to the compactification. And it could also miss decoupled modes, which are due to peculiarity of the compact manifold XP. Moreover, we cannot count if this manifold XP have defects. It would be hard. Integrating the anomaly polynomial will not capture such a data. So the approach we should do is then to sort of restart from the beginning, from a string theory setup, and try to better understand how anomalies can be computed for quantum field theories that we construct within string theory in general. So the outline of this talk is I will discuss some of the aspects of this work within the context of M-theory. Then topological math terms, which can appear, play a very important role. I will discuss their role and what they give for us. And then I will end with an example and some outlook. Our procedure could also be done for type 2B and F-theory. There will not be time. However, I include a couple of slides since the slides will be posted online for those who are curious how that works. So first, we consider a very general setup of 5 branes in M-theory. These could be flat. They could be probing singularities of various kinds, and they can be wrapped on some surface of various kinds to obtain 4D and 2D CFTs and the likes, or even 3D CFTs, although I will not say much. You can also do a combination of these things where 5 branes can wrap some manifold and then probe some singularities. All of these cases can give you a rich structure of quantum field theory. So in presence of the 5 brane, it is known that the M-theory, the 4-form flux for M-theory will admit some sources, which we denote as this. So W6 would be the whole volume of where the branes are. It is useful to split our M-theory background to an overall radial direction and then an internal and a space M10. M10 you can think of as a boundary of a tubular neighborhood that surrounds the branes themselves. So there's various basic things to define within this context, which is that first, M10 is a vibration with respect to some internal space over an external space-time W. So M10 minus D, which we will refer to as the internal space, has 2 components in general. There is a M4, which is the surrounding space of the brane. This is, for example, S4 in the case of the sphere, and X, which is some curve that could be wrapped by the branes themselves. M10, the space can be very non-trivial in many ways. In this analysis, it's allowed to have, for example, orbital fixed points, which can characterize some global symmetries. M4 is the vibration structure of M10 here is fixed by some topological twist, which you will need to preserve some SUSY in general case. So with this in mind, we can think about the symmetries of these problems in the following way. First, you can think about taking M-theory itself and reducing it on the internal space, M10 minus D. This could lead to very interesting gauge symmetry. These gauge symmetry will have various components. One is the isometry group of the internal space itself. And then you can look at massless fluctuations of the C3 potential expanded in some cohomology. In this case, we will not worry so much about torsion. I may say something about this later. Now, if you have this setup and then you restrict to the boundary of the space where there is some QFT that can live on the boundary and it lives on WD, the gauge symmetry in the bulk will imprint itself as some global symmetry. Now, because of the singular source of G4, if you study the classical variation of the M-Theory action in presence of such boundary, you find that it is itself anomalous. However, we know that this is a consistent quantum theory of gravity in all sense. And from long ago, we know also that the full theory, including the brain, since the brains are consistent sources for the theory, must be anomaly free. So this leads to the famous statement of anomaly inflow, which is that the quantum anomalies for the boundary degrees of freedom under the induced global symmetry from the bulk must cancel the classical bulk anomaly that we get from this supergravity. So what this tells us now, even though we may not have direct access or know what the boundary degrees of freedom of the theory are, of the quantum field theory, we can think about the bulk supergravity action in the bulk gravitational theory to actually extract the anomalies for the theory in the boundary. And this is the basic program that we run, and then we would like to understand what is the general statement we can make about the anomalies of CFTs, given the M10 minus D and its properties, given the internal space. Now, to study the variation of M-theory, due to the presence of this boundary condition, it is useful to take the full form G, and the leading term due to the boundary can be extracted in this way. So rho here is some bump function which vanishes far away. So G4 just has information of what's going on along this hard boundary. It is suitably quantized to be n as being the number of branes that are there. Now, to actually study the variation of the M-theory action due to this boundary, we must extend G4 to some form onto the full 10D tubular neighborhood boundary space. To do so, we have to introduce G4 gets extended to E4, where G4 is defined on the internal space. E4 is going to be defined on the full M10 space. Now, in defining E4, we have to explicitly gauge the action of the group G. So we have to gauge both the isometry group and also have a way of turning on fields that are associated to the symmetry from the fluctuation of the C3 potential. The point of view of this gauging, so we'll call that whole procedure gauging, on the world volume theory in the boundary on the brain, corresponds to turning on background fields, because these bulk fields that we turn on into the bulk supergravity, they have some Dirichlet boundary condition, which would correspond to the background fields that we would care about in trying to understand anomalies along the boundary theory. Now, with that object in hand, you can study the anomalous variation of M-theory in general. We can study the anomalous variation of M-theory, and the variation localizes on the boundary of the tubular neighborhoods of the brain, and is given by some local 10D form, which can be obtained through descent from a 12th anomaly form, I12, which we call the M-theory anomaly form. Not surprisingly, the anomalous variation of M-theory is coming from the Chern-Simons term of the M-theory itself. So this object can be expressed completely in terms of this extension of G4, which we call E4. And it includes various interesting terms. For example, it includes the X8 term, and this X8 term will allow us to capture things like gravitational anomaly in our system. Now, the inflow statement is the following, that we can then, once you obtain E4 and you constructed I12, you can integrate. It makes sense to take I12 and integrate it over the internal space. Then you would get an anomaly polynomial in lower dimensions, which captures an anomaly for some CFT or QFT, quantum field theory degrees of freedom. So the anomaly inflow statement is that if I take I inflow, which I compute from I12, plus the CFT anomaly, plus some potentially decoupled mode, which could correspond to center of mass mode, those things must add up to 0. So in this way, if you compute I inflow, you can say something about the anomaly of the CFT. In particular, if you're able to fix the decoupled mode completely, then you can fix the anomaly of the CFT exactly. So this object I inflow captures much more than just integrating anomaly polynomial of 6D series, for example. And this is this is a formal object from this point of view, but this is the object which we will use to extract some physical information. Now, to do an explicit example, consider M10 to be a 6D space times S4. So this would be the case for the flat branes. In this case, the symmetry that we care about is the SO5 symmetry, which is the isometry of this around sphere, which is also dual to the R symmetry of the 2-0 theory. In this case, you can E4 has an explicit expression, which we can flash to give you a sort of grounding, is that this first term here, you can recognize as the volume of the fourth sphere in embedding coordinates, and it is gauged over the SO5 connection, which is A5. And in extending G4 to E4, we must have a closed object, and that is also globally defined. We add suitable curvature terms, and you can see E4 can depend on the curvature explicitly and have 0 dependence on the internal space. And this object is the thing that now allows us to capture the anomaly of the 6D CFT. So in this case, when you then construct I12 and integrate it on the sphere, this was famously done in these papers. You have 2 terms. You obtain the anomaly of the 2-0 CFT plus a free tensor that decouples. In general, in our work, the general manifold M10 minus D has much less symmetry. It has a lot more structure present. We can expand E4 in general can be written as a sum of different terms, and each term is characterized by some cohomology group, and each term is an expansion along a basis along some basis of this cohomology group. Since we are not worrying so much about torsion, we can always pick a representative in de Rham cohomology and extract the coefficient n, which is a typical flux quantization coefficient that you would have for the 4-form flux. Now, from obtaining this object to constructing E4, which is a term that depends on the 4th cohomology group, you have your 4 forms, which, since we have a representative, we can gauge it over the isometry of the space. And the price we pay in gauging is we are forced to add curvature terms for the isometry group. And these curvature terms are, again, background fields that we would associate to this global symmetry on the field theory. And these terms are needed in order to impose closure of this object. So the closure of this E4 here is going to determine what this omega and this sigma are, and it will satisfy some constraints of this kind. Similarly, we can also, to give another example, we can consider if we expand E4 along the 2nd cohomology group, where we take 2 forms in this case, there we add a second piece, which is a scalar component, and then we have an F term. The F alpha here would be the background field associated to the U1s that you would get by expanding C3 along this guy. This also is subject to some constraint, which we give here. Now, the sum total of these equations is to tell you that the choice of E4 itself is going to be fixed by, E4 itself is fixed by picking a class in an equivariant cohomology group, in an equivariant cohomology of this internal space. more precisely, meaning that we can, for example, the anomaly that we compute is going to be independent of some exact deformations of these forms, among other things. There's also another field redefinition that you can sort of do. Since we're comparing, for example, E4, which has a 2 form here, you could imagine of taking the solution of this omega 2 form, which is associated to the 4 form, and you could shift it by something which is in the 2 cohomology. When you do such a shift, this would precisely correspond to doing a field redefinition of F alpha, which would be the background field associated to this U1 symmetry, which is going to be a non-R symmetry. So all of these things are summarized by saying that the E4 is fixed by a G equivariant cohomology of the internal space, where G here would be the isometry group. Does this thing hide? Now, in the end, we can compute our anomaly by considering local ansatz for the metric and P forms in the internal space. And we can impose various consistency conditions from the symmetry and topology of the internal space M10 minus D. So in constructing E4, we can impose regularity conditions on E4. And regularity conditions are going to be related to various integrals of the internal forms that we can do omega 4 and omega 2. And at the end of the day, when you put in all of this sort of topological and symmetry data in your construction of E4, the inflow anomaly will only depend on the background flux and background fields and various flux parameters that we get from M10 minus T. Now, even with that said, the expression that we get have to know something about the bulk supergravity. And we found that the way it can know about the physics of the bulk supergravity is obtained by imposing a tadpole condition, which is tantamount to imposing aspects of the equation of motion of the flux inside. But we don't need to impose the full local equation. We can just impose a tadpole condition associated with it. So this is more or less a summary of the program of how we can compute anomalies for CFTs by just looking at some internal space, M10 minus D. It is important to point out here, it's never in the case where we try to solve for equations of what this internal space explicitly is. It's just a more careful trying to track down what are the symmetries and what are the topologies of this space subject to the brane setup that we started with. And in the case, of course, so to sort of point out the role of this tadpole condition, there is a nice example which can be summarized in a slide, where let's consider E4. We could add to E4 some external 4 form, which onto the external spacetime, and we can consider this trying to compute anomalies for 6D series, for example. So in that case, when you compute I8 through this procedure, you find that this gamma 4 will have an explicit presence in the actual anomaly formula. And the tadpole condition will then fix gamma 4 to be this kind. This here is an explicit example where we look at 6D 1-0 theory that appear by taking 5 branes at an orbifold point. The G here are the symmetry groups that you get from the north and the south pole of the sphere, which have orbifold fixed points when I consider 5 branes at an orbifold fixed point. So this term here is actually quite important, and it contributes to the anomaly non-trivially. And indeed, this was also noted before in a very nice paper by these gentlemen, where they study the general anomaly of 1-0 series from 5 branes at an orbifold. There, just the inflow analysis that they did gave them the first term I8. However, the second term in the contribution here, which we obtained from our tadpole condition, they were able to sort of obtain it, but from a field theory analysis. And it's a field theory analysis where they add by hand a Green-Schwarz term, which is associated to the decoupled center of mass mode of the stack. Such sort of a physical field theory data is known by the bulk theory through this tadpole constraint. So the summary of this is that this tadpole constraint, what it's really doing, it will fix some components of the background fields. More specifically, the components that it will fix is going to be continuous components. It doesn't fix anything about the discrete parts of these gauge fields, which we will get to in a moment. And in a way, what it's doing is it's imposing the bulk equation of motions in a very, very weak way, in a way that is what you need to have a consistent anomaly for the boundary theory. So this method, we can also apply it whenever you have a holographic solution where there you have a conformal boundary instead of a hard boundary. And there you may not also know what is a local brane picture to describe such a system. So if you have some ADS D times M times solution in M-Theory, we can identify the internal space of such a solution with our M10 minus D, and the fluxes can also be identified. What this does is it allows us to extract topological and symmetry data, and we can construct E4 and compute I12. One of the nice upshots of this is that because our I12 also includes X8 terms and could also include higher derivative terms by construction, it will naturally give you one over n squared sort of corrections to the anomalies from this theory. It's also important here to highlight this sort of a construction is a very sort of UV picture of this quantum field theory. It is the data that you obtain from it is the data that you would obtain if you had some Lagrangian or some short distance physics. And of course, because you understand the topology of the internal space, and this should be preserved under RG flow, it also knows about if there would be any accidental symmetries that would emerge from below. So this computation is somewhere in between from what we usually think we can get in holography and what we think we can get from a Lagrangian picture of quantum field theory. And as such, of course, what it means though, even though when I compute I12 explicitly, if I want to get the central charges for my theory, which is a dynamical information, I would need to do extra maximization principle, whether it's in 4D or in 2D. However, this is a case where you're more confident that you've accounted for the symmetries of the problem when they appear. The terms that we don't get over here is the order 1 corrections, which are associated to decoupled center of mass modes of this system. However, there are some hints that this could be obtained in the next set of slides. So now we move on to the second part of topological mass terms and discrete symmetry. So often what happens is when we reduce M-theory on this internal space, we can have topological mass terms, and these signal spontaneous symmetry breaking of the bulk gauge symmetry. To be more explicit, let's consider, for example, 1 forms and 2 forms in a 6-dimensional internal space. So this would be a theory. The theory that you would get from such a thing would be a 4D CFT or 4D quantum field theory if you think about the decoupled modes. So the fluctuations of the 3 potential, you can have a 0 form gauge field. You can have a 2 form. You can have a gauge field for a 0 form symmetry, a gauge field for a 1 form symmetry, and a gauge field for a 2 form symmetry. When you look at the low energy Lagrangian that you get from the reduction of M-theory, the Chern-Simons term, for example, will give you topological mass terms, which are first order, which have one derivative term, but quadratic in the fields. Such a term, they signal that the gauge symmetry is spontaneously broken because these terms can be dualized to a Stickelberg mechanism. So the gauge symmetry associated to the B's here and A and C3 are actually broken in the low energy limit of the theory. And since we're computing anomalies for global symmetries, which have to come from good bulk gauge symmetries, we need to project out these things in some way. So interestingly enough, this is not something we should do by hand. The system should know how to do it on its own. And this is another role played by the tadpole conditions. This is a more physical way of understanding what these tadpole conditions are actually doing. What they do is that they will impose some relation between the background fields that we turn on, and those relations will exactly carry out the projecting, will exactly project out the degrees of freedom, or the fields that will project out the data that would be associated to these gauge symmetries that are spontaneously broken in the bulk of the theory. Okay. So now having these bulk gauge, these bulk topological mass terms are also interesting in other ways. In a suitable normalization of the gauge fields and from flux quantization, both omega and n are going to be integrally quantized. And from this point of view, we have the famous BF terms, which tells us why this can be thought of both as a spontaneously breaking of a continuous gauge symmetry, but also more importantly, it encodes discrete gauge symmetries for the 5D supergravity that you would get here. So in this example, where you have these choices N, A, as being coming from some internal fluxes of M-theory, you get both a ZK two-form symmetry and a ZK zero-form symmetry. K here is the greatest common divisor of NA, and this is an important point to have, because even though the gauge field can be suitably quantized, their fluxes can be suitably quantized. If you take a general linear combination, the general linear combination will also be integrally quantized. However, if the coefficients are co-prime, then you do not get any discrete gauge symmetry. So the discrete gauge symmetry is actually only related to the greatest common divisor, which can be factored out. So in this case, you would get a two-form ZK zero-form, two-form ZK symmetry, discrete symmetry, and a zero-form ZK symmetry. And from the B terms, you would get a ZM times ZM one-form symmetry associated. So these are bulk discrete gauge symmetries. They should have some, they should imprint themselves in the boundary to give you some discrete symmetry. However, here it's a bit more subtle. And it goes back to the nice paper of Witten discussing topological ADS-CFT and topological field theories. And the statement is that unlike the usual ADS-CFT, the boundary global symmetry that is dual to this discrete symmetry depends on the choice of a boundary condition for the gauge fields that you have, okay? And more precisely, because these actions are first order, you cannot impose both Dirichlet boundary conditions on both modes, on all of the modes at once. Then the theory would be trivial. But you can impose it on some of them to have a well-defined variational principle. In particular, if we, for example, impose Dirichlet boundary conditions on B1 fields, this will result in so this B1 field can then act as a source in an ADS-CFT sense for ZM global one-form symmetry, and the field theory would have then a ZM global one-form symmetry. Similarly, you can make a similar statement for the other fields that appear here. Interestingly enough, you can do something more fancy, you can consider mixed boundary conditions between the two forms B1 and B2 here. For example, if we take M, if M is a product of N1 and N2, you can pick B1 to have discrete boundary conditions which are valued in Zn sub 1. Then this allows you to also pick discrete boundary conditions for B2 in Zn sub 2, and then the boundary theory would have a Zn1 times Zn2 one-form global symmetry. Now, in our procedure, we can still use the anomaly polynomial that we computed in our procedure to actually say something about the 't Hooft anomalies related to these discrete symmetries. For example, if we look at the background fields, B1 and B2 in the anomaly polynomial, in the case of Zn1 times Zn2, we can read off the 't Hooft anomaly from the coefficient over here. Similarly, these background fields, these B background fields can also have terms with other symmetries in the anomaly. We could also read off the anomaly related to those guys too. So the topological mass terms allow us to understand better the sort of the role of the topological condition, but it also allow us to say some aspects of some of the discrete symmetries that appear for these for theories in the geometric engineering. Another important aspect of this, which is a third nice result that we get from thinking about the topological mass terms, is that in presence of a boundary, BF theories will admit singleton modes. So these are modes that are going to be pure gauge in the bulk of the theory, but then become dynamical in the boundary. So in particular, these would be modes that wouldn't contribute to the boundary stress tensor in ADS-CFT context. For example, if we consider a BF term, which is B wedge A, this will result into a P-1 form gauge field that is propagating in the boundary, which then corresponds to a U1 P-1, a U1 symmetry, which lives on the boundary. So in supersymmetric theories, such singletons that come from BF terms can have SUSY partners, and those SUSY partners are going to come from Kaluza-Klein singletons, which you can get from, let's say, reducing the metric and reducing the gravitino from upstairs, so you can get SUSY partners. And in cases where you have very little supersymmetry for n equal to 1 theories, actually the singletons that come from the Kaluza-Klein will not necessarily be in multiplets with respect to the BF terms, but they themselves will have their own role in the boundary theory. So in particular, there is a more physical way to interpret these singletons. And the way you should interpret them is that in the bulk, you have this spontaneous symmetry that is broken, that is associated to these BF terms. And if we pick a suitable boundary condition, we have a discrete symmetry for the boundary theory. So that discrete symmetry you should think of as actually coming from the spontaneous breaking of a global symmetry that was associated to the continuous symmetries in the bulk. From this point of view, the singletons do have duals in the boundary theory, and those duals you should think of as actually Goldstone modes associated to those global U1s that's been broken down. So this story is not so new, because we know, for example, in ADS 5 times S5, there's a singleton propagating in the boundary, which corresponds to a decoupled free n equal to 4 vector multiplets. Similarly, in the 2-0 theory, there's a singleton that's propagating in the boundary in ADS 7, which corresponds to a decoupled free tensor multiplet. So both of those you can understand as coming as goldstones that appear from the breaking of some higher form symmetry, both in the bulk and higher form symmetry in the bulk of the theory, and also in the boundary of the theory. And those, in those cases, of course, corresponds to the center of mass degree of freedom, and they should be subtracted off. So by looking at these BF terms and also studying the Kaluza-Klein singletons, you also have some data about the decoupled modes of the theory. So you can compute this part of the inflow data. And this gives you the order 1 information that you would want. Okay, so there is a rather nice discussion of this sort of idea in this paper of Mazzacena, Moore, and Seiberg. And in the case of the study of 5 branes and the compactification of the 5 branes, it turns out we can account for decoupling even when we take the 5 branes and do various twisted compactification on Riemann surfaces, and also compactification to 4D series. It turns out, if you look carefully at the singletons for those cases, you can account for the decoupling completely from the singletons. And our procedure in those cases completely fixes the anomaly of the 4D series that you would get in this way, simply by studying carefully the symmetries and the topology of the internal space. Unfortunately, actually, if you consider sort of orbifold theories, all the decoupling modes will not come from singletons. There will be additional modes which have more stringy nature, not Kaluza-Klein origin. And we hope to report on that later, not immediately. So this was nice because we can from the BF terms, we can actually study and understand what the decoupling is, and we can fix the anomaly for the CFT without having to have an explicit construction of this space M10 in an ADS CFT-like, or without even needing a sort of a Lagrangian for these series. Okay, so in the
you have 1 minute, please.
Oh, okay. So in the last minute, I'll try to zoom through an example. So we use this sort of technology to compute anomalies for punctured systems in class S, and we provide an alternate derivation of actually the puncture data in doing so. I will not say much. You can also explore punctures for more general classes of stories, but I will do one nice example, which I think encodes all of these things, if you allow me to have 1 more minute, is to consider, for example, a stack of 5 branes on a Riemann surface that are probing some Z2 orbifold fixed points. So in this case, the 6D space is M4 times sigma, where M4 is some resolution of the 4th sphere on top. So in this case, you get basically from the resolution 2 cycles, you can construct 4 cycles with the Riemann surface, and you have additional flux parameters that you can turn on. So there are 3 flux parameters in this system, and then you have associated closed 2 forms by Poincare duality. So the isometry here, you have a U1R symmetry, which is twisted over the Riemann surface, and then you have an SU2 flavor that appears. From the 6D theory, you can see a U1 times U1 that is coming from the resolution 2 cycle from the 6D theory. There is a third U1 that appears from this compactification, which is not transparent from the point of view of the 6D theory. So this is an accidental symmetry. And this third U1 is due to the fact that you have 3 closed 2 forms in the story. Now, there is also a topological mass term that appears for one combination of these U1s, which is not the original one that you started with. So the low energy limit, the low energy theory here actually is U1 squared, but the U1s that you start with the 6D theory are not the same that appears in the IR. These are shifted by the generator TC, which is this additional U1, which we interpret as accidental symmetry. So why is this important? This is important because of the presence of this shift, in 4D, the U1R symmetry will now mix non-trivially with these other guys. And when you account for this mixing, you then have to maximize to actually fix the central charge. And when you do that, you get a horrible expression in terms of the various fluxes of the theory. And magically, we can match that anomaly, those central charges, the anomaly data and the symmetry data, to a solution that's been known for a while, an ADS5 solution that's been known for a while, whose field theory duals have been missing. So by doing this sort of general analysis, we're able to construct the field theory duals of some interesting solution. And from the bulk analysis, we can see both a sort of a spontaneously symmetry breaking in the field theory along the flow. We can also see the emergence of accidental symmetries and the interplay in between them. So this theory is also quite interesting for other reasons, which we hope to report on soon, because of the actual space, it has a very rich, the cohomology group is highly non-trivial, which implies then a very rich discrete gauge symmetry in the bulk, which we summarize in this table. For example, you have one-form gauge field, three-form gauge fields, two-form gauge fields, and things that look like axion. And these discrete symmetries implies a very rich network of complex, discrete global symmetry for the CFT, which is acted upon by a non-trivial duality group, sp2z times z. And here we sort of summarize the discrete gauge symmetries because that is a simple thing to do. The choices that exist in the boundary is even more. Another interesting object that appears here, which we do not have a complete understanding yet, is in the reduction of the supergravity, there are these axion fields, and there are gradients, one form associated with these axion fields that appear as background fields into our anomaly formula. So to one forms, the suitable way to interpret them, they correspond to background fields for space-time dependent coupling. And the role of those objects, we do not yet have a complete picture, but we are studying, and those guys should be understood in this context of this very nice paper. So in this setup, we also have an explicit example that realizes some background dependent coupling, anomalies for background dependent coupling, which we hope to also study and report on soon. So on that note, I'll stop. And there's some outlook on trying to better understand the decoupling modes. And then there is various aspects of global anomalies and global aspects of symmetries that we hope to study and understand in this context. We can also do this for type 2b and F-theory compactification, which were worked out in this paper, and similarly for type 2a constructions. And the general message here is that this analysis relies less on SUSY, as originally the thing that we use to study field theories in geometric engineering, and we can use them to study more about punctures and defects and such an object. So I'll stop here. Thank you.
Okay, thank you. Do we have any questions? So in the meantime, I'll ask the first question. So you mentioned that in some cases there are decoupled modes that come from stringy modes and not from supergravity. So do you think there's maybe some way to lift this whole procedure to the full string theory and not just supergravity?
This is what we expect, but we don't have a clear path yet how to do it.
Okay, thank you.
Mm-hmm.
Any more questions? Okay, I don't see any questions, so let's thank the speaker again. And we have a break now, and the next session starts in 40 minutes. So people have time for breakfast, lunch, dinner, whatever.
Thanks, Ofer.
Can you see the cursor?
Yes.
Okay, that's good. All right.
All right, so you're on the live stream as well. Check that everybody that's supposed to be co-host is co-host. Okay, I think we're good to go.
Thank you.
Very nice. Mariana, you didn't have a train to catch today, right? It was tomorrow.
It's tomorrow, yeah.
Okay.
Yes. Yeah.
Okay, good.
Mariana, are you also from Cape Town?
No. I'm originally from Argentina, but I'm in France.
Okay. I see.
Okay, let's see. Let's take this down. Yifan, can I just share my screen for a little bit? I just want to put the advert for Shamit's talk up,
Yes.
so that people can see where to register, and then I'll pull it down.
Yeah, you can go ahead.
Okay, thanks.
Do I need to stop sharing?
No. As host, I'm a super user, so I can
Override.
overrule everything. What's up? You will have to reshare once I'm done.
Okay, that's fine.
Okay. So I'll just make a quick announcement and then we can. Okay. Hi, everybody. Welcome back to the second session of day 3 of Strings 2020. I just want to remind everybody that would like to attend. Shamit Kachru will be giving the public talk this evening at 8 o'clock. It is now 5 o'clock, so in 3 hours. And you can register on Zoom at the following address, strings2020.com/public talk. It will also live stream at the same place if you want to live stream instead. And I strongly urge everybody to attend if you can. Our session chair for the second session is Mariana Grania, who will introduce the speaker. Thank you.
Thank you, Jeff. Okay, now for the first speaker of this session is Yifan Wang, who's going to talk about taming defects in N=4 super Yang mills. Yifan, if you can share your screen.
Yeah, let me try sharing screen. Can you see the cursor?
Yeah.
Thank you. Thanks, Mariana, for the introduction. I would like to join the other speakers to thank the organizers for putting together this wonderful conference at this very special time, and also for the opportunity for me to speak here. So I'll be reporting on some recent progress in taming defects in interforce preamils. This will be based on 3 papers that appeared earlier this year. In particular, the second one with Shota Komatsu, a fantastic collaborator, and also some works in progress. So let me start with some brief motivations. So for the interforce preamils, it's perhaps the most well-studied interacting conformal field theory in recent years. And this is the case for several reasons. First of all, it shares many features of strongly coupled gauge theories in 4 dimensions. It also admits a variety of methods to study its dynamics, such as supersymmetric localization, integrability, and conformal bootstrap. Furthermore, thanks to the ADS-CFT correspondence, it bears close connection to quantum gravity on ADS5 times 5. And indeed, in recent years, there have been lots of progress made in determining basic observables in the interforce preamils as a conformal field theory, namely the correlation functions of local operators. But the spectrum of observables in interforce preamils is much richer than just the level of local correlators. In particular, it has defects of different codimensions. These defects are interesting and important observables for several reasons. First of all, they're sensitive to global structures of the gauge theory, which are otherwise invisible to local correlation functions. The defect also gave rise to new structure constants for the fully extended operator algebra. And by exploring general constraints on these new structure constants, such as coming from crossing and unitarity, we can formulate refined consistent conditions on a fully extended CFT. Perhaps the most familiar kind of defects in interforce preamils are the Wilson loop defects, also known as some other type defects. But more general defects in the interforce preamils are of the disorder type, some of which was already introduced in Charlotte's talk, such as the interface defect. These disorder defects are generally harder to study beyond perturbation theory, but we'll see how methods introduced in this talk will help us to handle these defects in general. Okay, so here is a general framework for a general program for studying defects in interforce preamils that one might envision. So first of all, we would like to have a classification of defects, or in other words, some universality class of defects, namely conformal defects in interforce preamils. To this end, there have been many partial classification results based on supersymmetric examples, such as the BPS-Wilson 2-Hooft loops, the Gukov-Witten surface operators, and Galto-Witten domain walls. Many of these defects also has holographic descriptions inside type 2 string theory. And this opens the way to potentially classify these defects by studying solutions to type 2 equation motion in the presence of suitable sources. Second on the list, we would like to develop some efficient tools to extract defect observables. So on one hand, we would like to have some analytic methods to determine defect structure constants. And we also want to combine this with potentially with the bootstrap philosophy, namely to formulate consistent conditions on the defect observables and explore constraints from unitarity and crossing, following these previous works. This bootstrap approach also gives potentially a bootstrap definition of conformal defects and allows a potential classification by exploring these bootstrap conditions. And finally, one would like to study implications from these defects for the fully extended CFT. So there are many applications. I'll just list a few here. The defects can generally be charged on the higher form symmetries. And as explained in Ibu's talk just now, these higher form symmetries can give rise to non-trivial anomalies in the fully extended theory. And this anomalies that when it involves these higher form symmetries can take incarnations on the defect volume through some particular couplings. We'll probably hear something along this line in Clay's talk. And finally, it will be an interesting question to understand what is the complete set of data to specify a fully extended CFT. So in some sense, this question will be related to classifying the kind of solution to the bootstrap conditions for defect observables. In this talk, I'll be modest and focus on the second point, that is to develop some analytic methods to extract defect observables. To be more concrete, let me focus on the inverse superamines theory with UN or SUN gauge group, and parameterize general observables in inverse superamines that may involve defects as follows. So here is the rank N of the gauge group, and here G4 is the Yang-Mills coupling, which I have combined with N into the total coupling for convenience. And the defect and this defect observables in general may preserve some or no supersymmetry, and that they lie somewhere on this axis. Depending where the observable sits in this parameter space, different efficient methods would apply. So two specific methods I'll introduce in this talk are the localization method and integrability method. The localization method applies when the defect observable of interest preserves the particular 1/16 pps subalgebra of the full superconformal algebra. If that's the case, then I'll describe an emergent 2D 1D description that allow you to efficiently extract such defect observable. On the other facets of this parameter space, namely at large N, we can use integrability to study defect observables. Traditional integrability approach start from this weak coupling limit that's based on the spin chain method. In this talk, I'll describe a bootstrap approach to integral boundary states that correspond to defects in the field theory. And this bootstrap program allows us to extract these defect observables, preserve no supersymmetry at finite coupling in the planar large N limit. And many of these results can be compared to predictions from type 2B string theory by a program analysis in type 2B on ADS 5.5, where we can trust the classical string theory description for large N and large total coupling. Applying these methods to the particular example, namely the 1-point function in the presence of interface defect, half PPS interface defect in inverse superamines, we can determine this 1-point function explicitly on these facets. And of course, the answers match at common regime of validity. And they also agree with the type string theory proposal. So in the end, we show that this defect 1-point function is completely determined on the dark regions of this parameter space. Of course, one would like to go deeper into this parameter space to probe more general defect observables, but that would require some other methods, potentially by conformal bootstrap along this line. But due to the time limit, I will not talk more about this in this talk. So let me start by talking about this localization method, which uncovers the emergent 2D 1D effective theory, which I'll call defect Yang-Mills theory, that is very useful to determine a large class of 1/16 pps defect observables in the inverse Yang-Mills theory. Before I give you some details of the defect Yang-Mills theory, I would like to briefly review two important previous works that led to the present development. The first is thanks to these authors here, where an emergent 2D subsector of the 4D super Yang-Mills on R4 or S4 was discovered. The emergent 2D Yang-Mills theory is restricted to the 0 instanton sector, 2D instanton. The gauge coupling of 2D Yang-Mills, G Yang-Mills squared, is related to the 4D gauge coupling as follows. The emergent Yang-Mills fields on this in this 2D sector lives on the particular S2 of size R. And these emergent 2D gauge fields are a combination of the 4D gauge field restricted to the S2 and a combination that involves 3 out of the 6 scalar in the super Yang-Mills theory. The main evidence for this 4D 2D correspondence comes originally from studying 1/8 BPS Wilson loops in the super Yang-Mills theory, and realizing that the similarly complicated observables can be reproduced by computing ordinary Wilson loop observables in the 2D Yang-Mills theory. And later, this picture was derived from a localization procedure, thanks to Pastun, by localizing the 4D super Yang-Mills theory S4 with respect to a particular supercharged Q that generates SU1/1 subalgebra of the full superconformal algebra PSU 2,2/4. This supercharged Q has a feature that is squares to a combination of a transverse rotation to the S2 inside S4, and also involves R symmetry rotation. This 4D 2D correspondence is very nice because it gives rise to a way to determine interacting, seemingly very complicated observable in the 4D super Yang-Mills theory by solvable methods in the 2D gauge theory, which is much simpler thanks to its quasi-topological nature. There's a very similar story that was later developed in the context of 3D for superconformal field theory on S3. There, thanks to the work of these people, it was discovered there's an emergent 1D topological quantum mechanics, a 1D subsector described by topological quantum mechanics on the grade S1 inside S3. The basic degree of freedom in this 1D topological quantum mechanics are some scalar fields, this Q and Q tilde. These are some antiperiodic scalars on S1, and they come from some twisted combination of hypermultiplets in the three-dimensional theory. You can make this picture more interesting by coupling the 3D hypermultiplets to some interacting vector multiplets. And by a non-trivial RG flow, such a UV description flows to interacting 3D superconformal field theory in IR. This corresponds to, on the 1D side, to upgrade from the topological quantum mechanics of free fields to some gauge topological quantum mechanics. And once again, this picture can be derived from localization by localizing respect to a supercharged Q3D that has a very simple that generates a very similar algebra inside now the 3D superconformal algebra OSP 4/4. And once again, this 3D 1D correspondence is very appealing because it gives a way to extract strongly coupled observables that may involve monopole operators, for example, and the vertex loops in the 3D for superconformal field theory, and reduce that problem to some solvable mini bootstrap problem in the 1D operator algebra. Many of these things are explored in these papers and also many others. Given the similarity between these two supercharges, there's one natural question you can ask. Can we combine these two setups in the one setting? This is especially natural because the 3D superconformal algebra OSP 4/4 it's naturally the symmetry of a half PPS superconformal interface defect in the inverter PMUs. And you can check, it's a simple exercise, that this is true. Namely, the 3D supercharge can be identified with the 4D supercharge Q that was used to identify the 2D subsector of 4D superMUs. Okay. And this very simple kinematic observation actually has interesting consequences. So first of all, of course, it puts these two previous setups in one setting, namely inverse superMUs in the presence of half PPS interface defect. But by studying the Q cohomology among general observables that involve arbitrary defects in inverse superMUs, it gives rise to a very rich zoo of observable in the Q cohomology. And by general principle, if you perform the localization of the superMUs theory in the presence of these defects which preserve the supercharged Q, it will give rise to some 2D MUs theory now, but it will be decorated by corresponding defect insertions. And I will call this defect enriched 2D MUs theory the defect MUs theory. Just to give you a flavor of what a general 116 PPS observable looks like in this setup, here is a picture where I have suppressed 2 directions out of the 4 directions in the super MUs theory. So one can have interface. So in the Q cohomology of the super MUs among the defect observables, one can have boundary defect or interface defect along equator S3. There can be surface operators, either transverse or longitudinal to the S2, where the 2D MUs lives. And also one can insert line operators of the Wilson loop type on the S2 of arbitrary contour, as well as Tohoft loops that on the circle that links with the S2. And there are also local operators you can insert on the S2, and as well as local operators restricted to the defect volume. And there's a very simple dictionary that translates between the 4D defect observables to defect observable in the 2D MUs theory. Some of the defect observables in 4D will modify the 2D MUs theory, such as boundary interface will correspond to some boundary interface coupling on the equator S1 inside S2. And surface operator, if it's transverse to the S2, will give rise to some codimension 2 twist operators on S2. If it's longitudinal, it will correspond to Higgs in the gauge group of the 2D MUs theory to some Levy subgroup. Similarly, Wilson loops in the 4D super MUs simply map to Wilson loops in the 2D MUs theory. But Tohoft loops are more interesting. It modifies the 2D MUs path integral by including unstable 2D instantons, which are absent in the pair to the M theory that I introduced in the beginning. Local operators also has a simple explanation in the 2D description. They just correspond to some field strength insertions. Due to the time limit of this talk, I'll be focusing on the case of the boundary interface defect, possibly in the presence of some local operator insertions, just to illustrate this machinery. So as I promised, now let's move on to application, to the case of a DeFi brain interface defect in virtual PMUs. This kind of interface defect was already talked about in Charlotte's talk, so I'll be brief on this. So this DeFi brain interface can be easily engineered in type 2B string theory by the simplest kind will be a single DeFi brain intersecting with a stack of D3 brains. Because the D3 brains can end on a DeFi brain, so on either side of the DeFi brain located at x1 equals 0, we can have a different number of D3 brains. And there's also S-dual picture, thanks to the S-duality in type 2B string theory, where the DeFi brain is replaced by an S5 brain that extends in 3 other transverse directions. The 2 setups preserve the same superconformal symmetry. The description of the interface defect in the super MUs Lagrangian is also very simple. Because there's a different number of D3 brains on 2 sides of the DeFi brain, the interface defect interpolates between super MUs theory of different rank, say between UN and UN plus K. And K parameterizes the type of this DeFi brain interface. More specifically, the field configuration in the super MUs in the presence of the DeFi brain interface looks like follows. So let me split the 6 scalars of the super MUs theory into 2 triplets, X and Y. Most of the fields in the super MUs theory satisfy a continuity condition across the defect. This includes the gauge fields and the Y scalars. Plus and minus means it is to the right or to the left of the defect. The dotted entries are unconstrained, but otherwise obey some standard regularity condition. On the other hand, the X scalars are allowed to develop a pole as we approach the interface from the right. And the pole takes a very special form, the simple pole in X1 as X1 approaches 0. The polar coefficient is a triplet of matrices which have to satisfy IC2 commutation relation to preserve the superconformal symmetry. And just up to a gauge transformation, UK gauge transformation, you can put the third component of this triplet of matrices into this diagonal form. And this is what is normally referred to as the non-pole configuration. This non-pole configuration is, of course, very, very explicit, but it's kind of hard to use. I mean, because it's like an intrinsic disorder type defect, it's hard to use if you want to do any computation beyond perturbation theory. But fortunately, there's a mirror description of the same interface defect, thanks to the work of Galto and Witten. As explained in this paper, there's an alternative 3-4 Lagrangian theory, a UV description, as some quiver gauge theory that flows to the same non-pole type defect in IR. The quiver is a linear quiver that looks like follows, with manifest 3D4 supersymmetry. The nodes of the quiver are unitary gauge groups, and each edge corresponds to a bifundamental hypermultiplet. In particular, this quiver has an enhanced global symmetry in IR that's enhanced from the topological symmetry associated with each of these unitary nodes, and such that the total symmetry becomes the UN plus K times UN global symmetry. This enhancement is crucial for coupling this interface theory to the dynamical fields in the bulk of the 4D super MUs. And the coupling is very natural just by gauging the boundary modes of UN plus K super MUs on one side and the boundary modes of the UN super MUs on the other side. And this gluing picture together defines the UV Lagrangian for the super MUs theory on S4 in the presence of a DeFi brain interface at the equator. And the construction is such that it is guaranteed to preserve the supercharged Q, the particular supercharged Q that generates a subalgebra inside OSP 4/4 preserved by the interface, and the full superconformal algebra PSU 2,2/4. And once you have this Lagrangian and the desired supercharge, one can just run the localization. I will spare you the details and just present the results. After some algebra, what you can show is that there's an emergent 2D, 1D path integral that captures all the dynamics of observable in the Q cohomology in the superammules. The path integral looks like follows. They involve some 2D gauge fields on the two hemispheres, A and A prime, and also some 1D emergent degrees freedom on the equator. The 1D degrees freedom are, the dynamics of 1D degree freedom is captured by some complicated 1D action, and also has non-trivial couplings to the gauge fields on the two hemispheres. The action of the 2D gauge fields are just given by the usual Yang-Mills action in 2D. And with this 2D 1D path integral in hand, we are ready to use it to compute general 116 BPS observables in the superammules theory in the presence of DeFi brain interface, which is taken care of by this kind of coupling. So let me just apply this to the most basic observable in the presence of a DeFi brain interface, namely the defect 1-point function of a bulk operator in the presence of this interface defect. This is the very basic observable in the presence of defect because, for example, general correlation functions of local operators in the presence of this interface can be obtained by first taking a bulk OBE limit and expand into this simple defect structure constants. There's a very strong constraint from conformal identity on such 1-point functions. First of all, the 1-point function is 0 unless the operator you insert is a scalar. Furthermore, the position dependence of this scalar 1-point function is also completely fixed by the distance as perp between the insertion and the defect. So the physics is just contained in its coefficients, which I've circled here. And this is the object we're after. So for simplicity, let me restrict ourselves to the case where this operator is a half BPS operator into our superammules. And it carries a particular R charge J with respect to a U1 subgroup of the SO6 R symmetry, and it has dimension J thanks to the BPS condition. And it can be explicitly written in terms of some 2 of the 6 scalars inside superammules, a single trace operator. And following the general dictionary I introduced before, I sketched it before, this 1-point function in the full superammules theory with this interface defect can be computed by some 2D 1D path integral, where this insertion just translates to insertion of field strength in the 2D path integral. Okay. And the strategy to determine this observable is first to integrate out this 1D fields, Q and Q tilde, and that gives rise to some potentially complicated 2D effective theory. But by some standard 2D gauge theory techniques, you can massage this 2D path integral into a simple matrix model. So let me just show you the results. The 1-point function, or the 1-point function of a half BPS operator OJ in the presence of dimension J in the presence of this half BPS interface of DeFi brain type, labeled by K, meaning that interpolates between UN and UN plus K superammules theory, takes the form of a simple matrix model, where the matrix degree freedom comes from an end-to-end Hermitian matrix, and A are the eigenvalues. This delta A is the familiar Vandermonde determinant. And this insertion here in the square bracket corresponds to the insertion OJ in the expectation value. Namely, these Fs are degree J polynomials, which is related to the Chebyshev polynomial, which come from usual Gram-Schmidt procedure. Of course, we also have the 1-point function of the bare defect in the absence of any local operator insertion, and takes a very simple form. And you can obtain a normalized 1-point function of the OJ operator by taking the ratio. We can be more explicit in the large N limit, where we can solve the matrix model using the saddle point approximation in the strict large limit. The answer looks very simple. I receive a contribution from some integral and from a sum. The integral part takes slightly different forms depending on whether K, which labels the DeFi brain interface, is odd or even. Here, G is just the square root, is related to the square root of the 't Hooft coupling. And there's also an interesting sum contribution, which has an interesting structure. It's a sum of over K entries. And what's more interesting is that, I mean, this sum will have an interpretation from later part of the talk from the interoperability side. But moreover, is the appearance of some Joukowsky variable XS, which is related to the subscript as follows. It depends on the gauge coupling. And the Joukowsky variables arises naturally in the interoperability literature And this is already some hint for potential interoperability of this DeFi brain interface, which we'll explore later in this talk. And with these very explicit expressions in hand, we can do some easy checks. For example, if you, so these expressions are exact in the lambda, but otherwise in the larger limit. You can expand the expression in the large lambda limit and compare with type 2B string theory predictions. So in that context, the computation boils down to some probe DeFi brain analysis on ADS4 times S2 with k units of world volume flux, threading is S2. And the one-point function can be extracted by studying world volume couplings on the DeFi brain world volume action by being careful about couplings to closed string KK modes. And of course, one can do a small lambda expansion as well and check with perturbation theory. And this checks works out nicely. Let's now move on to the second topic. That is a bootstrap approach to integral boundary states that correspond to interface defects in first preambles. Before I talk about this boundary approach to integral boundary states, let me just briefly review this more traditional approach using interoperability to study defect observables. And that is based on the integral string chain language. The setup of the integral string chain starts with realizing that the single trace operators are related to a string chain. So for simplicity, I'll restrict ourselves to the so-called SU2 sector, where the single trace operator are built out of two complex scalars in the superambiguous theory, Z and Y. And the ground state of the spin chain correspond to the single trace operator with just Z insertions. And the Y insertions correspond to the so-called magnons, which can be thought of as excitations on the spin chain. In this context, the defect can be represented by a particular matrix product state, as was talked about in Charlot's talk. This single trace operator, on the other hand, correspond to a beta eigenstates. And they're labeled by rapidities, UM of the magnons, which essentially keep track of the Y insertions. And one-point functions simply come from the overlap in the spin chain. But this method, unfortunately, is limited to weak coupling, because in the spin chain description, one implicitly assumes that there's a nearest neighbor next to nearest neighbor couplings. And such restriction is not sensible if we want to consider finite coupling. So to overcome these limitations, we upgrade from integrable string chain to integrable quantum field theory. Where does this integrable quantum field theory arise? It arises naturally on the worldsheet of the type 2B string theory on ADS5 times 5. More specifically, the DeFi brain interface defect in the large n limit would naturally correspond to a boundary state on the worldsheet of the type 2B string theory on ADS5 times 5. The integral field theory that I was talking about would arise when you take the Green-Schwarz string and in the light cone limit, where the effective theory is described by, on the worldsheet, it's described by 8 massive fermions and 8 massive bosons. The single trace operators in that context correspond to a closed string state on the worldsheet. And the one-point function are just computed by some overlap between this boundary state and this closed string state. A natural question that one may ask is that in this integrable field theory, is this boundary state also integrable? Indeed, there are some evidences from the weak coupling analysis thanks to the spin chain method. For example, the overlap between these two states computed from the spin chain method is only non-vanishing if the rapidities pair up. So the rapidities should be interpreted as so the magnon should be interpreted as particles on this in this integrable field theory on the worldsheet, and the rapidities are related to the momentum of these particles. The fact that the rapidity have to pair up for a non-trivial overlap means that there's essentially no particle production in this reflection process if you rotate this diagram by 90 degrees more precisely. And there's also a finer structure of this observable computed from the spin chain method, namely always involve a ratio of Gaussian determinants, which basically computes norm of this beta eigenstates. And as argued in this paper, these are very strong evidence for this boundary state to be integrable. Okay, so given that it's an integrable boundary state, we can apply this bootstrap philosophy to bootstrap such an integrable boundary state. This bootstrap philosophy is not new. It was first introduced, I guess, almost 30 years ago by Gosho and Zamolodchikov, and more recently explored in this very nice paper. In particular, interoperability implies that the general overlaps between this boundary state and the closed string state will factorize into two-particle overlaps. And one can explore symmetry constraints on these two-particle overlaps. Here is the sum SU2/1 subalgebra squared inside the more familiar SU2/2 squared algebra preserved by two-point functions that's familiar in the interoperability literature. And then we would like to explore consistent conditions, further consistent conditions on these two-particle overlaps, say coming from boundary Yang-Baxter equation, which basically says that whenever two particles cross, you have to pay a price by the bulk 2-2 S matrix. And there's also a boundary unitarity constraint, which is most easy to understand if you rotate the diagram by 90 degrees. You're supposed to sum over these intermediate particles, and it's just correspond to some insertion of complete set of states in this picture. And moreover, there's a Watson condition, which basically says that whenever two particles cross, you have to pay a price by S matrix, a bulk S matrix. And with these general constraints listed, one can then proceed to solve these constraints by applying the bootstrap philosophy. The answer looks like follows. So for simplicity, I'll restrict to the so-called SU2 sector that I mentioned before. That means it determines correlation functions or overlaps between the boundary state and the local operators that are built out of just two complex scalars z and y. And the length of this operator, meaning the number of letters, will be L. And the R charge of this operator will be determined by the number of z, which I'll call J. The expressions are particularly simple in the large J limit. It takes the following form. So the structure, the position dependence is completely fixed. And the interesting thing is this coefficient, the structure constant. The structure constant takes a very interesting form. It's a sum over overlaps between this closed string state with some component boundary state. This is very interesting in the sense that from the string theory perspective, the boundary states that correspond to the interface defects comes in SU2 multiplet of size k. And from this bootstrap analysis, one can see that this different boundary states in this k multiplet are related by potential bound states between a given boundary state and the particle states. And most of these explicit factors in this expression keep track of the kinematics of this rapidities of this y magnons. The coupling dependence is hidden in the colored factors. So this TK is the so-called flux vector, which inherits the sum structure. I just want to point out that this quantity is precisely the Joukowsky coordinates XA that also appeared in the localization results. And this is not a surprise, and it's a consistency check. And this sigma parameter is the so-called dressing phase for the boundary state, which we determined from the boundary bootstrap. And this sigma tilde is a combination of dressing phase for the bulk 2-2 S matrix. And this is determined from some previous work from Bicert and others. And this G plus and G minus are the Gaussian determinants, which essentially determines the norm of this closed string state. And they're also completely determined by studying the asymptotic, by studying the beta equation. And this, I should say that this kinematic structure in the dependence on U was recently extended to the full SO6 sector by these authors. Okay? SO6 means that this all operator can be built out of any scalar inside Super Yang-Mills sphere. And there's some immediate checks one can do. For example, if you look at zero Magnan case, which correspond to the ground state on the spin chain, or the BPS closed string state, and that of course matches with the large J BPS one-point function. And one can also do a weak coupling expansion of this. So everything here is exact in the 't Hooft coupling. You can do a weak coupling expansion, and that agrees with the spin chain method. And there's some more checks explored in this more recent paper. And to go beyond this expression, I should say these expressions are exact in the large J limit and to all orders in the 1/J expansion. But if you want to go beyond that, consider finite J, you have to take into account the non-perturbed defects in J, and that's the so-called wrapping corrections or Lucia corrections. The idea is that this closed string worldsheet has a transverse size that's proportional to J. And in the large J limit, the wrapping corrections are suppressed. The wrapping corrections are coming from virtual particles going around this string. But this wrapping correction can be systematically extracted using the TBA and analytic continuation method. Let me just summarize. So as I promised, I presented to you a toolkit for studying defects in inverse preambles. First of all, there's a localization method that allows extraction of general 116 PPS defect networks in inverse preambles for arbitrary gauge group and arbitrary coupling. There's also a complementary method by a bootstrap approach to integral boundary states that take care of non-BPS correlation functions, but in the strict large n limit, but otherwise arbitrary to Hooft coupling. And I've illustrated the power of these methods in the context of a particular application to one-point function in the inverse preambles in the presence of a half BPS DeFi brain interface. So there are a lot more applications and potentially interesting future directions. Let me just comment on several of them. So first of all, this formalism that I discussed can be applied to study correlation functions of both bulk and defect, bulk operators and defect operators that are restricted to the defect world volume. Some of the localization method was already explored in this earlier paper. We can also upgrade from this topologically more trivial manifold like S4 or R4 to some topologically more interesting manifold like RP4. In that case, the emergent 2D theory would naturally leave on RP2 some manifold in RP4, as was discussed in this paper. And we also like to study other defects, such as surface defects, and potentially surface defects linked with line defects. Such configuration, because of non-trivial topology, is sensitive to global structure of the gauge theory and topological couplings. And more generally, we would like to develop a explicit map between discrete theta angles in the 4D Yamil's theory, as well as topological terms to such quantities in 2D defect Yamil's theory. Okay. On the other front, we would like to have some classification of integral boundary states, given how powerful it is in this DeFi brain interface context. We would like to have a classification of general integral boundary states in the context of type 2B string theory ADS 5x5. This will be a complementary approach. Well, on the ADS 5x5, this should be a promising approach to study, say, for example, de-instantine effects, and also some more exotic defects in super Yamil's theory, say coming from D7 brain, as Charlotte talked about. Slightly related, topological defects, or sometimes called bibrains, on worldsheet sigma models are known to generate new boundary states, starting from a given boundary states in the open string field theory language, as explored in these papers. It'll be interesting to explore if there's any relation to interface defects in the super Yamil's theory. There have been lots of recent interest in studying TD bar deformations, but mostly in the context of 2D quantum field theories or 2D conformal field theories. There has been some recent proposal for a TD bar-like deformation for the inverse preambles, but very little is known about the physical nature of this deformation, such as inclusibility. Fortunately, thanks to this 2D 4D map, which I've reviewed, we can relate such a TD bar deformation in 2D Yamil's theory. And turns out that 2D Yamil's theory does have a solvable TD bar deformation explored in this paper. And it'll be interesting to study the consequence of this in light of this 2D 4D relation for the 4D inverse preambles under TD bar deformation. And of course, it'll be interesting to study SL2Z properties of this general defect observables. There have been a lot of recent progress in understanding SL2Z properties of correlation functions of local operators, where non-trivial modular invariance can be obtained by studying this 4-point function in the large n limit. Including defects will definitely enrich the story, and this will be something worth exploring. And finally, it will be interesting to extend this defect analysis to other ADS CFT pairs, in particular in the context of ADS3 CFT correspondence, as was explained in Rajesh's talk. Beyond deriving ADS CFT, so ADS3 CFT2 beyond the level of local operators, we would like to include also defects. And because in this context, the 2D CFD technology can be applied both at the spacetime and worldsheet level, it holds the promise of actually deriving this in the presence of defect insertions on the field theory side. So there are many more applications I'll be happy to discuss after the talk. But let me end here. Thank you and invite questions.
Okay, let's unmute ourselves for a few seconds to thank Yifan for that very nice talk. And questions. There was some question by Juan Martin Maldacena in the chat. Do you want to ask the question?
Let me see chat.
I was just simply asking how you determine the normalization, but I see that Shota was gave me an answer.
Okay, the normalization of the one-point functions?
Yeah, the overall normalization of the boundary state.
Right. Yeah, that's essentially related to this insertion in the matrix model. So it's normalized by the two-point function.
Any questions? Any other questions? Yeah, Hi,
Yifan.
Yes.
So does the localization result shed light on the integrability beyond the leading large N limit?
That's a very good question. Well, I mean, we haven't really studied the 1/over correction to the localization results. I would say potentially, but generally it's very, as you know, the going beyond the planar limit is very difficult. I mean, Shota and Joao has some work on that by including more handles. But
because here you can potentially have many explicit formula. Maybe.
That's right. Yes, I think definitely that's something worth exploring. Yes.
Edwin.
So the 1/16 BPS Wilson operators that you consider, what sort of loops on S4 can they live on?
Right. So it can live anywhere. So let me give you the picture. So this is the S2. The Wilson loop can live anywhere on S2. They can intersect. It can be arbitrary contour.
Anywhere, but only on the S2.
That's right. That's right. To preserve the Q. Well, so that's a large class, but there are also another class of Wilson loops that preserve the symmetry supercharge that locates on the circle that links with S2. But I did not discuss it here.
Thank you.
You can find it in my original paper.
Any other question?
So sorry, can I ask you a question, please?
Yes, go ahead, please.
So how about descendant operators? So do you actually do any operator in the D3-D5 setup?
Sorry, what about what operator? I missed the first.
Descendant. So we usually study beta states. So overlaps of beta states, but do you actually consider any beta states of any calls for superior means, or just the specific states that you just showed us?
Oh, so the explicit analysis that I presented is restrict to the so-called SU2 sector.
Right.
Yeah, but this analysis, the kinematics dependence on the rapidities was extended, I guess, by a paper that appeared 2 days ago to the full SO6 sector. I don't know about the, for example, SU2/3. I mean, those things can be definitely worked out, but we didn't do it in our paper. But yeah, I think it's a simple exercise to work it out. What's harder will be this wrapping corrections, namely non-perturbative corrections in J. That requires more work.
All right. Thanks.
Yeah.
Any other questions?
How do boundary or interface local operators work in integrability?
That's a very good question. So this is something work in progress with Shota. So I would suspect it corresponds to some open string excitations. We only have some localization results so far. So I don't have anything concrete to say on the integrability side at the moment.
Yeah, Maldacena. You have another question?
Another observable in these defect operators is the 2-point function of the displacement operator. Is
very
that
good question. Very good question. I haven't checked it very carefully, but I believe the displacement operator itself is not in the Q cohomology, but it can be related to some other observables that do live in the Q cohomology.
Okay, thank you.
Yeah.
Any other questions? No. Well, if not, let's thank Yifan again. And we have a little break, and we resume at 6 p.m. South African time, whatever time is it for you. Is Clay co-host?
Not yet. I will make him one now.
Okay. Very nice talk, Yifan, by the way. Very interesting.
Thank you.
Yeah, I have some, but if nobody asks, I have some silly questions. Why does the flavor symmetry enhance in the infrared?
Oh, so those are coming from monopole operators. So there's a manifest topological U1 symmetry coming from each unitary node. But there are also monopole operators that give rise to extra flavor currents in IR.
Oh, I see.
Yeah.
Where is that crucial then?
Oh, right, because the way that, because you want to couple this theory to some 4D gauge theory with non-abelian gauge groups, right? I mean, in particular, the coupling should be gauge invariant. And the way you want to couple them is, I mean, the natural way to couple them is if your 3D theory actually has these global symmetries that you can gauge.
Yeah,
if you just have U1s, that would not be possible to have a gauge invariant coupling.
I see, I see. And about integrability, you don't want to disclose anything else?
Well, I mean, depending on which thing you want to ask me about integrability on the last slide. I mean, there are many venues to explore. So something we find very exciting is for the D-instanton boundary states.
Say that again?
For D-instanton boundary states, AES5-5. So as Xi and Ashok told us about, I mean, doing this D-instanton computation from honest perturbation string theory is very difficult on flat space. But on AES5-5, there's an advantage. I mean, there's a disadvantage. Namely, there's no convenient worldsheet description, the CFT description. But there's also an advantage, meaning that the presence of the non-trivial geometry actually gives rise to a mass to some effective description, effective fields on the worldsheet. So there's integrable field theory with massive particles. And if the boundary state is indeed integrable, you can bootstrap it using this procedure that I outlined for D fiber interface, but now apply to the D-1 instanton at a fixed location. And then you can compute the one-point function in the presence of d-1 instanton at a fixed location. And then this allows you to compute some disk diagrams. And then if this works, then you can just integrate over the instant moduli and get the, whatever you want to know about correlation function in the presence of the instantons in for superamials.
Can one consider also one-point functions of operators in the presence of Wilson loops?
Right, yeah, yes. So you mean a one-point function transfers to the Wilson loop?
Yeah, that's right. It's a closed string operator inserted
right.
in the Wilson loop.
Right. I'm not sure, but maybe this was already studied in some recent paper from Shota and Simone. I'm not very sure, but there's a recent paper that appeared that discussed similar setups. Right. Nice diagram.
Yeah, thank you. Just found it in the internet. I thought there should be an African background.
South Africa.
It's quite inspired.
Yeah, I should also say that this interoperability is not proven at the level of this Green-Schwarz light cone gauge Wilshire theory. There's a lot of motivation. I mean, there's many checks by comparing to the spin chain. And hopefully this recent development, thanks to the work of Costello and Stefanski, I hope I spelled his name correctly. There's a potential way to prove interoperability of the Green-Schwarz string in ADS5-5.
Yeah, but okay, we all believe it, right?
Sorry?
We all believe it.
But I would have said that to some extent, integrability is, in this case, in typical of this ADS background, is what defines the quantum Green-Schwarz string beyond the leading orders. Because I would usually think of the Green-Schwarz string as an effective action that is sort of the most general thing you can write down to leading order in a derivative expansion that's consistent with the spontaneously broken super-punctuated symmetry in space-time. But as you know, beyond the leading field orders, you're going to have terms that involve extrinsic curvature and so forth. That would be a priori ambiguous, right. And nobody has actually attempted to directly quantize Green-Schwarz to the loop order in alpha prime that would encounter this ambiguity. And integrability, in some sense, would fix that ambiguity for you.
Yes, but one would like to show that this is the only sensible prescription to fix this ambiguity. And I was saying that this kind of setup from Costello and
do you mean by demanding that it's a dual of the gauge theory, or in what sense? I mean, if you're just talking about the string theory background, you think that the integral background is a unique background that has the right isometry, the super isometry?
Yeah, that I'm not sure.
Hi, Clay. Do you want to just good?
Jeff, no more announcements to make?
No, I think we're okay.
Okay.
About 5 minutes It's enough time to grab some coffee.
Yeah.
मन जाते तो अच्छा।
Still have a couple of minutes.
Mariana, is my mic working?
Yep, yep. Yeah. Are you ready?
Sure.
Okay, so let's resume. We're happy to have Clay Cordova from Chicago, who's going to talk about higher group symmetry and applications.
All right, thanks everyone. Thanks to the organizers for giving me this opportunity. Today I'm going to introduce you to this concept of higher group symmetry, which is something that I've been thinking about for the last couple of years. And I'll give you kind of a smorgasbord of applications to various different aspects of quantum field theory. Before getting started, I'd like to just give a shout out to all my great collaborators that I've been lucky to work with over the last 2 years. Here they are. And let me also flash some references. So my starting point in this subject was introduced in the first 2 papers on this list, which came out about 1.5 years ago. And then some of the applications that I'll talk about today are based on these next 2 papers, which will hopefully appear both very soon. And I'd also like to point out some foundational work in this area that was done in papers by Kapustin and Thorngren, and also closely related ideas in the condensed matter literature by Barkeshli, Bonderson, Cheng, and Wang, and also work by Tachikawa. Okay, so what is the big picture? What are we trying to do? So the kind of motivation is that symmetry, that is global symmetry, is one of the few universally applicable tools to constrain quantum field theories and their dynamics. And what we would like to do is to explore symmetry, generally speaking. So what symmetry principles exist, and we'd like to kind of go deep down and understand how these can be used to constrain dynamics of quantum field theories. So one important new development in this area in the last few years has been generalized global symmetry. So this is a powerful new organizing principle. And what's generalized about it? Well, we have, in this terminology, we have ordinary, that is 0 form global symmetries, and these act on local operators, and everybody's familiar with these. And then we also have higher form global symmetries, and these are characterized by their actions on extended defects. And the kind of big picture of this talk is we'd like to understand what possible mixings can occur when we have both types of symmetries, that is ordinary global symmetry and higher form global symmetry. And you could think that this is sort of an analog of looking for non-abelian structures in these symmetries. And what we'll see is that higher group global symmetry is one general possibility for mixing of form symmetries of different degrees. And I'll introduce this concept and then apply it to a bunch of different seemingly disparate questions. Okay, so let's get started with some more technical details. So a continuous Q-form global symmetry is characterized by the existence of a Q+1 form conserved current. We'll call it J superscript Q+1. It has Q+1 indices. It is totally anti-symmetric, and it is conserved. The currents are a good way to characterize continuous global symmetry. Of course, all of these concepts also exist for discrete global symmetry, where the currents aren't as useful. And then we'll have to invent a new perspective, which we'll talk about a little bit later. The charged objects under a Q-form global symmetry are extended operators of dimension Q. So for Q equals 0, that's the case of ordinary global symmetry. These are point operators. For Q equals 1, these are line operators. And for Q equals 2, these are surface operators. And if you've never seen this before, it might seem very abstract, but a basic example to sort of latch onto and make everything feel quite concrete is 4D abelian gauge theory. That is just free Maxwell theory. In this theory, we have the Bianchi identity and the free equation of motion, and these imply both that F is conserved and that star F is conserved. So F here is the field strength. And so by this definition on this page, we conclude that Maxwell theory has one form global symmetry, which is U1 times U1. So what are the charged operators under these symmetries? The charged operators are Wilson and 't Hooft lines. And to say that an operator is charged means that if you have a two-sphere that links a line L, and you put this integral of this current on the 2-sphere, then you can unlink the sphere on the line at the expense of a phase, which you think of as the charge of the line. So here's the geometry in pictures. We have the red 2-sphere. It's linked with the blue line. We can unlink them and collapse the sphere and remove the insertion of the integral of the current at the expense of a phase. And in Maxwell theory, this is true by Gauss's laws. Okay, now we've talked about currents. In general, when you're studying global symmetry, it's also useful to couple to background gauge fields. And this leads to a partition function. The partition function is a function of the background gauge field. So I'll call the background gauge field sometimes A, and Z will be a function of big A. And in this discussion, it's important to remember that A is a fixed classical source. And for a continuous symmetry, Z of A is a generating function of correlation functions for the current J. So at least a first approximation, that's how you think of the partition function. Now, higher form global symmetry currents naturally couple to gauge fields with more indices. So for instance, a 1-form symmetry couples to a 2-form current B, just in the standard way. B contracts with the indices of J. And now current conservation means that the partition function Z of B, which we think of as a function of this background 2-form gauge field, is invariant under gauge transformations with a 1-form gauge parameter, lambda 1. And of course, like other notions of symmetry, this invariance could be violated by 't Hooft anomalies. Okay, so we've done a little warm up. We've talked about ordinary global symmetry a little bit. We've introduced 1-form symmetry. And now we could ask a kind of innocuous question. Let's take simple interacting theory, 4D QED. So we have a U1 gauge theory with NF fermions of charge Q. And we could ask, what is the symmetry of this quantum field theory? This is a basic question that we hope to be able to answer. Well, there are certain pieces of it that are obvious. So first of all, there's the SUNF left times SUNF right ordinary global symmetry that acts on the left and right-handed Weyl fermions. And finally, well, in addition, there's also this, there's also 1-form symmetry. We mentioned previously that Maxwell theory had U1 times U1 1-form symmetry. Here, one of those currents is gone because of the charged matter. F is no longer conserved, but star F is conserved by the Bianchi identity. So there's still a U1 1-form symmetry, which we can think of as measuring magnetic charge. So we have this U1 1-form symmetry, and we've got this non-abelian ordinary global symmetry. And naively, you might expect that these things don't talk to each other, but in fact, they mix. And this mixing is basically the key thing that we want to zoom in on in the rest of the talk. So one way to diagnose the mixing and this interesting behavior is to examine a triangle diagram. So in this case, it will be a triangle diagram with where the legs are 2 flavor current insertions, that is the ordinary global symmetry flavor current insertions, and an insertion of a dynamical gauge field. Now I remind you that triangle diagrams, like we study in QFT textbooks, have various different interpretations depending on whether the vertices couple dynamical gauge fields or current for flavor symmetries. So let's just quickly go through them. So perhaps the most familiar one is the one where all 3 vertices are dynamical gauge fields. This is often called the gauge anomaly. And this must vanish if the theory is going to be mathematically consistent. The next is where we have 2 gauge vertices and 1 flavor vertices. And this is sometimes called the ABJ anomaly. And if it's non-zero, it means that the flavor symmetry is broken. Another much discussed triangle diagram in recent times is flavor cubed anomalies. These are 't Hooft anomalies. They mean the flavor symmetry is unbroken, but these have the important implication that they match along RG flows and constraint dynamics. And finally, we come to the situation that we're discussing here, where we have 2 flavor insertions and 1 gauge insertion. This means that the flavor symmetry is unbroken. And what we will see is that the implication of this kind of triangle diagram is that it deforms the current algebra between the flavor symmetry and the 1-form symmetry. And it's this deformed current algebra that we're defining as higher group global symmetry. So in this case, it's called a 2-group. the higher group is called a 2 group because the highest form current involved has 2 indices. And this also matches with some previous existing mathematics literature about this subject. Okay, so I advertise that there's some current algebra. Let's get a little bit more explicit about what it is. So the mixing between the ordinary 0-form global symmetry and the 1-form global symmetry in this example is encoded in a 3-point function where we have 2 ordinary global symmetry currents and 1-form global symmetry current. That's this 3-point function here. And you should think that looking at this 3-point function is analogous to what you do when you look for at the 3-point function of ordinary global symmetries to find the non-abelian structure constants. So here we're doing something quite similar. So what do we have? Precisely we have Ward identities relating this 3-point function to the 2-point function here of 2 1-form global symmetries. It's easiest to state this Ward identities on a special locus in momentum space where p squared is q squared is p plus q squared. So the 2-point function is easy to constrain. There is some tensor structure here. There's some tensor structure that's completely determined by conservation. I won't write it. And then there's a structure function f of p squared over m squared, where m is some scale. And the Ward identity that we are talking about relates that same structure function to a particular structure in the 3-point function. So in this 3-point function, we have some other tensor here. We have some to contract some group theory indices. We have the same f of p squared over m squared, the same structure function. And then we have a very important coefficient kappa that we'll discuss a little bit more below. And QED, 4D QED, realizes these identities with kappa equal to q, the charge of the fermions, and the currents given by what we discussed before. So you can also think of these Ward identities as being a consequence of certain important contact terms in the operator product expansion of 2 ordinary currents. So we could take the divergence of an ordinary current and collide it with another current. Now, the ordinary global symmetry is a symmetry of this problem. So the divergence of that current is 0 at separated points. So when we collide it with another operator, we can at most expect to find a contact term. And there is one very natural contact term that you can find, which I've written here. So it has the 1-form global symmetry current appearing on the right-hand side, some derivative of a delta function, and then again this structure constant kappa. And we're going to see that this structure constant kappa is something analogous to like FABC and Lie algebra. It's what's specifying the deformation of the current algebra. Now, let me remind you that you may be familiar with these kind of contact terms in the OPE of a current, and they're typically associated with charged operators. So usually you have the divergence of the current hits a local operator and returns something proportional to the charge of that operator. And in the operator product expansion that I mentioned above, related to the higher group, there's a derivative on the delta function. And this means that the global charge algebra is not modified, even though the current algebra is deformed. So these Ward identities and OPEs give us one way to think about what this deformed current algebra, this higher group symmetry is. But there's also another way, which is background fields. So if we have both an ordinary global symmetry and a 1-form global symmetry, for instance, the appropriate background fields are, at least locally, a 1-form gauge field A and a 2-form gauge field big B. And if we have this higher group symmetry structure, these now mix under gauge transformations. So here, A, the ordinary global symmetry background field, has a standard gauge transformation. The first part of the transformation for the 1-form symmetry background looks standard, but now there's a new piece. So this constant kappa appears, and also the gauge parameter small lambda appears, and the gauge field small a, big A appears. And if you're thinking, gee, this formula looks familiar, you're right. What this is a Green-Shorts transformation for background fields. So usually when you think about the Green-Schwarz mechanism, you have in mind some kind of some dynamical B field, which has the kind of interesting gauge transformation rule that's cooked up to cancel some important anomaly. And here we have something similar, but actually logically prior. We have the situation where those dynamical fields are not yet, those fields, that B field is not yet dynamical, but is rather background. And so the important point is that if you have this kind of global symmetry, this higher group global symmetry, the modified transformations above make the partition function Z, which is now a function of both capital A and capital B, they make it invariant, of course, up to C number anomalies. Okay, so what's in this name, higher group? Well, for instance, in mathematics, this pair A1, B2, together with the gluing rule specified by the gauge transformations, is called a two connection on a two group bundle. That's one place where we got this name. And one important general feature is that this structure constant kappa must be quantized in integer units. How do we see that? Well, one way to see it is to look again at this Green-Schwarz transformation for B. And here what you see is something kind of funny. You see that a naked gauge parameter lambda appears. Usually when you see gauge parameters, they occur with derivatives. And there's a good reason they occur with derivatives is because the gauge parameters are ambiguous. When you go around to one cycle, little lambda could shift by 2 pi times an integer. So this formula here looks a bit suspect because of that. But in fact, all is well. If kappa is an integer, then that ambiguity can be compensated for by a gauge transformation involving big lambda 1. So that's why we need kappa to be integer quantized. And let me just briefly comment that when you generalize this kind of structure from the simple example that I'm giving here to ordinary discrete zero form groups G and other discrete one form groups K, you find again an analog of this this structure kappa, and you find that it's some element of a group cohomology class. Some element of group cohomology. Okay, so I've introduced this concept of higher group symmetry, and once you get here, you find that higher group symmetry is in many ways similar to ordinary global symmetry. So what do I mean? I mean that first of all, various groups are possible. The zero form symmetry can be abelian and non-abelian. Both the zero form and higher form symmetry could be discrete. This higher group global symmetry could be emergent. It could pop out along an RG flow. It can be spontaneously broken. And it can also have 't Hooft anomalies, which have their own universe of classification and match along RG flows and constrain dynamics. And so in the rest of the talk, I'd like to take this concept of higher group symmetry and apply it to a couple different cases and show you a little more. So the first thing I'd like to tell you about is how do you think about this notion when the symmetries are, say, discrete and you don't have currents? So this was a subject of a paper that I wrote with Benini and Sin. So the way to proceed here is that you characterize the global symmetry in these examples in terms of symmetry defects. So symmetry defects are very useful objects for thinking about discrete symmetries because you don't have currents. So what are the rules? So there are kind of there are various important rules. So first of all, the zero form symmetry defect is a codimension 1 object. A 1 form symmetry defect is a codimension 2 object in your theory, and so forth. And what are the rules? Here they are. So if you take an operator phi and you move it across a symmetry defect labeled by some group element G, then you implement the group transformation G times phi. The defects are topological. So if you deform the shape of the defect, it stays the same. That's supposed to replace the notion of current conservation. And finally, why do they form a group? Well, the group is encoded in the fusion law. So if you have a defect G and a defect H and you collide them, you'll get a defect for the composite group element. Okay, so these symmetry defects give you actually a way to encode higher group global symmetry just abstractly in terms of the fusion algebra of these defects. So let me explain it to you in the case of a 2 group. The case of a higher group is quite similar. So let's let G be the 0 form symmetry and A the 1 form symmetry. And then if you have a quantum field theory that occurs in 3 space-time dimensions and above, you cannot avoid the situation where 3 global symmetry defects intersect. So here I've drawn a picture where 3 global zero-form symmetry defects intersect. So we have G, we have H, and we have K. Their pairwise intersections are shown in red. And their codimension 3 triple intersection is shown at this black dot. And what can happen is that at that black dot, a 1-form global symmetry defect can emerge. This is shown in blue. And this emergence, this possible fusion algebra is characterized, in fact, by a group cohomology class in H3 of G with coefficients in A, and that is how you think about abstractly this higher group in this case. Okay, so this is not just a purely kind of abstract nonsense discussion. It actually has some explicit consequences, both in 3D Chern-Simons matter theories and in 3D TQFTs. So this has been somewhat discussed in the condensed matter literature. For instance, in 3D TQFTs, these are characterized by a modular tensor category. And the most natural setup where this the situation that I was talking about occurs is that you have G, the zero-form global symmetry, is the automorphism of this modular tensor category, and A, the 1-form symmetry, are the abelian anyons of the theory. And then the action of G on A actually encodes typically a 2-group global symmetry. So this is a ubiquitous phenomenon in topological quantum field theories. Okay, so I've now given you some discrete examples of higher groups and explained how to think about them. And now I'd like to move on to a different topic and a different application of this notion. And this new application is some constraints on emergent symmetry that you can derive using higher group global symmetry. So let's suppose we have the very general situation where we have a renormalization group flow where the ultraviolet does not have a higher group global symmetry, but the infrared does. Now in this situation, we can think that there's an energy scale EQ below which the Q form symmetry is effectively respected. So it's difficult to define EQ exactly, but we can certainly talk about scales far above EQ where the symmetry is gone and scales far below EQ where the symmetry is present in the effective field theory. And one way to think about this is that in the EFT that's applicable below the scale EQ, there are Q-dimensional defects charged under the emergent symmetry. And at the scale EQ, these defects become the world volumes of new dynamical degrees of freedom. So for instance, if we are talking about a 2-form global symmetry, which we will be momentarily, there are charged surface operators at long distances, and at the scale E2, you could resolve these the thickness of these objects, and you could think of them as the world volume of dynamical strings. And it's the fluctuations of these dynamical strings that destroy the symmetry, this 2-form symmetry above this scale E2. Okay, so now suppose you have this situation, but you're talking about a higher group symmetry, i.e. a non-zero value of this structure constant kappa. Then what you can show is that in this situation, the scales EQ obey a very general inequality, E0 less than or equal to E1, less than or equal to E2, etc. How can we understand this? Well, one way to understand this is by examining the transformation rules for the background fields. So for instance, let's return to the example that we introduced explicitly, this 2-group transformations. What do you see? You see that because of this Green-Schwarz term, the gauge transformations of the ordinary gauge field A activate the background field B of the 1-form symmetry. Therefore, if the 0-form symmetry is present and you can couple to A, the 1-form symmetry must also be present so that you can couple to B. So that's an instance of this kind of inequality, E0 less than or equal to E1. And by generalizing this argument, you can argue for this nested sequence of inequalities in general. So it turns out that axions provide a kind of cute set of examples to illustrate these constraints on emergent symmetry. So what's an axion for my purposes? For my purposes, an axion is a periodic scalar field A with some periodicity 2 pi f. And all such theories have an interesting two-form global symmetry with current J3 ABC that is star dA. And the charged objects are surfaces, surface defects, with the feature that as you integrate dA around them, you get a multiple of the periodicity, where the integer multiple n appearing there is the charge of the defect. Okay, so what's the scale E2 in this situation? The scale E2 is where the two-form symmetry is broken, and we expect some new fields in this effective field theory. For instance, A may become the angular part of a complex scalar phi, where the radial part of phi is liberated at the scale E2. That would be one possibility. And parametrically, you expect that E2 scales like F, but these, of course, may differ by some dimensionless couplings. Okay, so the key point is that in models where axions couple to non-abelian gauge fields, there is in fact a higher group global symmetry. So let's consider a very standard axion Yang-Mills Lagrangian. So we've got some gauge kinetic term for some SUN gauge fields. We've got a kinetic term for our axion field. And then A couples to the instanton density as A trace F wedge F. And the scale F appears in the denominator. Okay, so the axion has the two-form symmetry that we discussed before, but the SUN gauge fields themselves also have an interesting higher form symmetry. They have a ZN one-form symmetry, a discrete one-form symmetry. And this ZN one-form symmetry, what does it act on? Well, it measures the charges of Wilson lines. So in this example, there's no dynamical fundamental matter. There's only adjoint matter. So Wilson lines in the fundamental cannot be screened. And that gives us this ZN one-form symmetry as a good quantum number. Okay, so then given that there's this higher group as demonstrated in these two papers here, we would deduce from our previous discussion a very general inequality on any UV completion of this model, which is that E1 that is less than or equal to E2. So what are these scales? Well, we mentioned that E2 is the scale where the strings become dynamical. What is E1? E1 is the scale associated to the one-form symmetry. That's where charged fundamental matter appears. Okay, so let's see how this is enforced in a explicit concrete example. So we could look at a Kim, Schiffman, Weinstein, Zakharov axion model. And this arises from an action of a very standard form. So here we have a gauge kinetic term. We have some fundamental fermions psi. They're in the fundamental of SUN. And then there's also a neutral scalar phi. Phi couples to these fermions with a Yukawa coupling. And then there's also a kind of Mexican hat type potential with quartic coupling M. Okay, so if you just quickly analyze this model, what you find is that, well, the minimum of the absolute value of phi is at F, at least superficially. And then plugging in and turning the crank, you would find that this model leads to axion Yang-Mills at long distances, where because of a Pecha-Quinn type mechanism, where A becomes the angular part of phi, and the decay constant is F. Okay, so then you could look at this model and you could examine this constraint that we had derived before, E1 less than or equal to E2. And what you would conclude is that if you want axion Yang-Mills to really be the effective field theory, then you need lambda, the Yukawa coupling, to be less than or equal to M, at least parametrically, the quartic coupling. So that's by comparing the scales at which the fermions come back and the scales at which the radial part of phi comes back. So how is this enforced? So there are a couple ways you could try to violate it. So one way is you could just try to go to strong coupling. Of course, then I can't say anything. But it's actually more illuminating to see what happens if you try to violate this inequality at weak coupling. So we could take both lambda and M, both the Yukawa and the quartic coupling, to be tiny, but take them to be in the reverse hierarchy. So the Yukawa coupling much greater than the quartic. And then what you find is that there is a quartic, there is a one loop contribution to the potential for the radial mode. So this one loop contribution moves the minimum of the potential from F to above the UV cutoff. So it moves lambda, it moves the minimum of the radial mode to big lambda, the UV cutoff, divided by small lambda. And so what this means is that at low energies, the angular mode A is effectively non-compact, right? The periodicity of A has become larger than the UV cutoff of your theory. And so this thing no longer interacts with the gluons. So this is basically illustrating this inequality. If we want to have the K NSVZ model flow to axion-Yang mills, we need this inequality on the Yukawa and the quartic. Okay, so that's the end of this topic. The final topic where I'll apply higher group global symmetry is to 6-dimensional quantum field theories. And this is the subject of some upcoming work with Dumitrescu and Intriligator, building on a series of works by us in this subject. So what's the basic paradigm of these quantum field theories? So 6D SCFTs and little string theories, well, they have the feature that at long distances, they tip on their moduli space, they look like gauge theories, often non-abelian gauge theories. And the fixed point that one is interested in talking about is in the ultraviolet. And by now, many, maybe even all, examples of this SCFTs and little string theories have been constructed in F-theory in a sequence of papers by Vafa, Heckman, and many others. Also, Rodelius and Morrison's name should be in there. Okay, so why am I talking about these? Well, in the infrared effective field theory, there's of these models, there is always an interesting one-form global symmetry. What is it? So you take trace F wedge F for the non-abelian gauge field, take star of it, and that gives you a two-form conserved current. This is present ubiquitously. So we could ask, are these one-form global symmetries also present in the ultraviolet fixed point, whether it be a SCFT or a little string theory, and do they form any interesting higher group structure? So we'll see that there's a kind of bifurcation depending on whether the ultraviolet is a superconformal fixed point or a little string theory. So let's discuss the first case where the UV is a conformal fixed point. So in this case, there are dynamical tensor multiplets that are crucial. And these have bosonic fields, which are a real scalar that I call rho, and a dynamical fluctuating two-form gauge field small b. Small b should not be confused with big B. The action necessarily includes couplings of the following form. Rho times the kinetic term for F squared. So why is that one necessarily there? Well, it's because without that, the gauge kinetic term would break conformal invariance. So by making the coupling dynamical, that is by having rho multiply the kinetic term, you can try to restore conformal invariance. And then crucially, that coupling has a super partner, which is this small b coupling to J, this instanton current. So when you look at this action, what you see is that the one-form symmetry that we were talking about is in fact gauged. It couples to a dynamical gauge field. And so we expect that it disappears in the ultraviolet superconformal field theory. We expect there is no one-form symmetry there because of this coupling. And in fact, this is the case and could be demonstrated in a completely different abstract way. Simply look at the unitary representations of the appropriate superconformal group in 6 dimensions. And what you find is there are no unitary representations that can contain this one-form global symmetry current. So there are no such currents at all in any 6D SCFT. There's no one-form global symmetry. And then, of course, because of that, there are no continuous higher groups. So that's the situation for conformal field theories. And the way I phrased it just now, it sounds like a negative result. There's no higher form global symmetry. And and there's no or continuous one-form symmetry, and there's no higher group symmetry. But this negative result actually has some important implications. So recall that from our previous discussion that we could fix the higher group structure constants by examining mixed anomaly terms involving flavor or asymmetry gauge fields, background gauge fields, and dynamical gauge fields. So what we learned from this discussion is that the mixed anomaly coefficients, those that would imply a non-zero higher group structure, non-trivial higher group structure, must in fact all vanish in any superconformal field theory. So that's what I've written here. We have 0 equals the mixed total anomaly. Now this mixed total anomaly, if you're working on the moduli space, it looks like it splits into two pieces. One is easy to determine. This is the contribution from the matter fields that you just get by looking at the various representations, gauge groups, etc. And then there's another that's harder to figure out. It's how it comes from how the dynamical B fields come to couple to these background gauge fields. These are the Green-Schwarz contributions. And so a priori, you might not know what fixes these Green-Schwarz contributions. But in fact, by this equation, because the left-hand side is known to be 0, the right-hand side is also, and this term is fixed, this mixed contribution is also fixed. So to summarize, what does that mean? It means that all 't Hooft anomalies of the ultraviolet superconformal field theory are fixed completely by the IR moduli space gauge theory description. And this matches very nicely with an earlier proposal by Omori, Shimizu, Tachikawa, and Yonekura.
You have 5 minutes, Clay.
So we can also use our new knowledge about the 't Hooft anomalies to prove some other general results about 60 SCFTs. So for instance, using supersymmetry, we can determine all of the conformal anomalies of 60 SCFTs purely from their IR moduli space, because supersymmetry relates the 't Hooft anomalies to the conformal anomalies. So this means, for instance, that the 2- and 3-point functions of the energy momentum tensor at the fixed point are completely determined just from the moduli space matter content. We can also learn something interesting about the A-type conformal anomaly. This A-type conformal anomaly features in the A theorem, which is of course still partly conjectural in 6 dimensions. But what we can show using our method, our moduli space method for computing A, is that we can show that for all 60 SCFTs, A is necessarily non-negative. And this dovetails very nicely with the idea that A is a kind of measure of the degrees of freedom of a superconformal fixed point. Okay, so that's everything I wanted to say about SCFTs. Let me make some final comments about little string theories and how higher group symmetry is prominent there. So let's consider, for example, the type 2b 1-1 little string theory. This arises from the decoupling limit of NS5 branes. And in this case, the low energy effective field theory is super Yang-Mills with gauge group SUN, where N is the number of branes. And we can look at this instanton current. Oops, there's a typo. It should read J2 is star trace F wedge F. And this measures the fundamental string charge. So in fact, because it measures the fundamental string charge, which we know to be a good quantum number in string theory, we expect it to be present along the entire RG flow. And in particular, the background B field that we've harped on so much, the background field for the one-form symmetry, this has a very physical interpretation in this example. It's simply the decoupled NS&S sector B field from type 2B string theory. So we expect this one-form symmetry to be present in the little string theory. And these theories, of course, also have SU2 times SU2R symmetry. And it's natural to ask whether these symmetries are assembled into a higher group. And the answer, of course, is yes. Otherwise, I wouldn't be telling you. So since there's no tensors, no dynamical tensors in this example, there's no Green-Schwarz couplings to worry about. And we can read off the structure constants of the higher group from box diagrams involving the infrared gauge fields. So these are box diagrams, which have 2 flavor insertions and 2 gauge insertions. And in this case, you find terms of the form I8 mixed Well, there's a second Chern class of the dynamical gauge field C2 of F. Then it's multiplied by a difference of second Chern classes for the two R symmetries, R1 and R2. And then you have N, that number of branes appearing there. And so because this is non-zero, we have a non-trivial higher group in this little string theory. And we have all of its ensuing ward identities that I discussed before, which are relations on momentum space correlators for the little string theory. So it would be interesting to think more about those. And this appears to be ubiquitous, this presence of higher group symmetry in little string theory. So for instance, just to throw out one other example, the SO32 small instantons have a rich higher group structure involving both the flavor, Lorentz, and one form symmetry, all of which are mixed together, and there are lots of ward identities there. Okay, so I've finished. Let me conclude and highlight a couple interesting open directions. So I hope I've convinced you that higher group global symmetry plays a prominent role in many quantum field theories. These include three-dimensional Chern-Simons matter theories and topological field theories, 4D gauge theories, models of axions, superconformal fixed points in d greater than 4, and probably many others that I didn't even think about. And higher group global symmetry may also be a useful tool to organize little string theories, maybe into some kind of something like universality classes. Now, there are many open directions to explore, and many other people are working on related topics, but let me just highlight two that I thought are particularly interesting that I didn't get to talk about. So one is that we talked about higher group global symmetry as a global symmetry, where you have just background fields. But it's quite interesting to promote these background fields to be dynamical. And this is especially useful in the case of discrete symmetries. This leads to a very interesting, rich class of topological field theories that has recently been explored, for instance, by Thorngren. And finally, let me also mention some work in progress, is that in 4 dimensions, there's a close connection between two-group global symmetry and some aspects of the Kalland-Rubakov effect. And I hope to have an opportunity to tell you about that in the future. Thanks very much.
Let's thank Clay for that very nice talk. Questions, Nathan Cyber?
Yes, so regarding the little string theory, it doesn't really have meaningful local operators. So how do you think of the objects that participate in the...
Yeah, excellent question. So my understanding is that it doesn't have local operators, but it does have momentum space, suitably smeared momentum space correlation functions. So those are some class of good observables. So I think that these ward identities in momentum space, smeared versions of them still have interesting implications. But let me stay on that kind of safe ground.
So the danger, of course, is that if you try to take these momentum modes and reassemble them into coordinate space operators, then...
Yes, that is not supposed to work. So
well, it doesn't work because different components get different renormalization.
Yeah.
So I'm not quite sure what will happen. So are you going to do everything only in momentum space, or what do you have in mind?
Well, I certainly have in mind that in momentum space, the ward identities that we wrote down at the beginning still apply to little string theory. But if you ask me to pin down what are the complete list of meaningful momentum space observables that you're allowed to study, that I don't know the answer to. I think maybe some experts in little string theory do, though.
So I have a variant of this question. What are the charged objects under this symmetry, especially in the context of the little string theory?
That's a good question. So so I don't know the physical description of the answer in little string theory, but I think that's somewhat related to the second open direction work that is being discussed here. So I think the right answer, which we're working on, is ray operators. So like a line that ends at a point. And that smells like the right answer, because the line might be able to talk to the one form symmetry, and the point might be able to talk to the zero form symmetry. And so if you can look at some kind of rays together, maybe with some, or maybe even junctions between like operators that live on the line, those are the right notions of charged objects. But that's sort of the subject of this second work in progress.
And should this be meaningful in the context of closed string theory?
Well, that would be very interesting if the answer is yes. Yeah, I think, I mean, you know, that one form symmetry, when it acts on the vacuum, I guess you could think that it makes a little string. So, so this is like, would be some kind of domain wall in the little string. That's a good, yeah, I haven't thought about it too much beyond that.
Okay, Yifan Wang.
Hi, Clay. Nice talk. So I have a follow-up question about little string.
Okay.
So many of this little string theory, I mean, whether it's 1, 0, 2, 0 supersymmetry, or 1, 1, they have a holographic description in either type 2P or heterotic string. So do you know how this two-group structure will show up on the worldsheet, in the worldsheet description?
In the worldsheet, no, I'm not sure. That's an interesting question.
So have you already determined this two-group for, you know, say the 2, 0, 1, 1 type little string theories?
Yeah. So for instance, here, this was from this formula here, you can read off what it is in the 1, 1 type 2B little string.
I see.
Yeah. We haven't explored in complete generality. Just a few examples to note that it's sort of all over the place. I mean, once there's no theorem forbidding it, then you should expect it. And that's kind of the general mantra in this higher group global symmetry in general, is that if you have zero form symmetry and higher form symmetry, or if you have form symmetries of different degrees, unless you have some specific reason to expect that they factorize, they typically form a higher group.
I see.
Davide Gallotto has a question.
Hi. So you mentioned the one form symmetry structure involving the Lorentz group. Is this something that can happen?
So what I mean is that the ordinary global symmetry is the analog of the zero form symmetry in the higher group is being played by Lorentz symmetry.
Is this something that can happen in a local theory, or is it special to?
No, it can happen. It can happen in a local theory. It can even.
Did we lose Clay? Clay, we lost you. Seems like we lost the speaker. Okay, I guess we should end it there. Chef, can you see the local organizers? Can you see what's wrong?
I can't. I don't see Clay on the list of participants right now.
Okay.
Yeah, I think we might have lost.
Perhaps some of his collaborators who are around could answer questions.
Yeah, that's a good idea. Do we have any more questions?
No, Davide was asking, I mean, Clay was answering Davide.
Oh, hello.
Ken is
hello.
here.
Yeah.
Hello.
Yeah, I guess Clay was talking about the contribution from gravitational anomalies that can.
Hello, 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 hello. Hello.
Hello, I seem to have disappeared from planet Earth for briefly. I'm not sure why, but am I back to being host? I can go back to sharing the screen. Sorry about that. I don't know what happened.
You should be able to share your screen anyway.
Okay, got it. David, are you still there?
Yes.
Oh, you're here. Okay, so I was giving you an example answer to your question, which was about an example of a higher group involving the Lorentz symmetry, the Poincare symmetry, and some one-form symmetry. So a cute example is to consider U1 gauge theory in 4 dimensions. And you consider 4 fermions with charges 3, 4, 5, and -6. Now this theory is consistent because of this cute equation, 3 cubed plus 4 cubed plus 5 cubed is 6 cubed. So the U1 gauge anomaly is 0. There's a one-form symmetry, again, associated to the current star F, the magnetic one. And now the B field transforms under local Lorentz transformations. The reason is that the sum of these charges, 3, 4, 5, and -6, is not 0. So the sum of the charges is exactly what occurs in a triangle diagram where you have 2 stress tensor insertions and 1 gauge field insertion. So this gives an example where the higher group is mixed. Not sure who's drawing on my screen. That's interesting. With the Poincare symmetry.
Okay, Davide,
I see. Thank you.
And Yifan, you have another question?
Yes, if I may.
Yes.
So Clay, I have another question. So as you know, the theory on the 2,0 tensor branch has different UV completions, either by the 2,0 superconfluent field theory or by the 2,0 little string theory. The 2 UV completions differ by certain higher derivative couplings.
Yes.
I was wondering if this 2-group structure that you find can help you to constrain what kind of higher derivative terms there should be there.
That's a nice question. Yeah, that's a nice question. But it sounds
For example,
like
as you know, the trace f to the 4th is absent in one case. But
yeah. Yeah, I mean, it sounds like there might be something there. I haven't thought about that before, but yeah, you might wonder if the trace f to the 4th being there or not can break the ward identities that I was talking about.
Right.
And I'm not sure. That's a good question. Yeah.
Okay. Thank you.
Any other question? Yes, Gurulashmi Subramanian.
Hi, thanks for the nice talk. So I was just curious to know, so when we just promote these global symmetries to dynamical fields, do we still get, so for example, the mixed anomaly term generated by the Green-Schwarz, that term, is that still, that cannot be fixed, right? For the dynamical.
It's not something to be fixed or not. It's not a bug. It's just a feature. So if you promote A and B to be dynamical, then you want to sum over A's and B's modulo gauge transformations. You want to sum over them modulo these gauge transformations. Just like when you have an ordinary symmetry and you promote A to be dynamical, you want to sum over A modulo this ordinary gauge transformation.
I see. Okay.
Any other question? Okay, if not, let's thank Clay again. Clap.
Yeah.
And all the speakers of today. And Jeff, I don't know if you want to announce again the public talk.
Yeah. So thank you, Mariana, for the chairing, and thank you for the speakers. Thank you to the speakers for today. So just a reminder that in just a little over an hour, Shamit Kachru will be giving a public talk. Let me display again the advert for the talk for anyone who wants it. So here's the ad for the talk. You can register on Zoom because it's a public talk. We thought we'd open the registration via Zoom and not via this conference. So to register, just go to strings2020.com/public talk, and you'll get an email confirming your registration and with the Zoom link to link to, or I will turn the live stream off shortly, and then we'll turn it back on again for the talk. So the link for the live stream is the same as usual. So we'll have a about an hour break, and for those of you who are joining us for the public talk, we'll see you again in an hour.